Welcome, everyone. This is Michael Gibbs, and I'm the founder and CEO of Go Cloud Architects and Go Cloud Careers. And I'm so excited to be back here with you today on the third day of our AWS Certified Solution Architect Associate Bootcamp 2022. And this is a free, full AWS course to help you prepare for the SAA-CO2 exam. My name is Michael Gibbs. I'll be your instructor for this week. For those of you that know me, which is most of you, you know that I've been working in tech now for over 25 years, and I've been a network architect, an enterprise architect, and a cloud architect for as long as I can remember, and these architecture careers are the greatest thing ever, and I absolutely love every last one of them. I love every minute I've spent in my architecture career for the last few decades, and I want you all to have the best cloud architect careers and solution architect careers so you can have the life, a wonderful life, just like I had. So before we begin, let's go through the housekeeping things. This is our free AWS Certified Solution Architect Associate, day 3. You can go back if you've missed day 1 or day 2. They're completely recorded. You can visit them on the YouTube channel, and we'd love to share them with you. Additionally, I want to let you know that if you have not gotten your copy of our free AWS Certified Solution Architect Associate Professional book, please download your free copy. I mean, it's a book. People love this book. They're talking about it everywhere. Over 400 press outlets shared the book because they loved it so much. We have people coming to us telling us they've already been past their Certified Solution Architect Professional just by reading this book, and it's only been out there for a few days. So go out there and get your completely free AWS Certified Solution Architect Professional exam guide. Now, when we're dealing with cloud computing, we're dealing with a network and a data center that's been virtualized. And in order to understand it, you need to understand the network a little bit. So what we're going to do is we're going to host in the end of January, completely free, a Cisco Certified Network Associate program that's going to be tailored for the cloud architect. And we want you to be there, obviously, because we want you all to get cloud hard. I want you to be the best cloud architects, solutions architects, enterprise architects, or any kind of architect job you absolutely desire. So we're going to do that. It's going to be completely free. Now, next week, we're going to invite you to a Cloud Architect Challenge. And on this Cloud Architect Challenge or experience, we'll invite you, and you'll get to live the real life of a cloud architect. You will ask me, who will be the CEO of a business, about my business goals, my business pain points, my business challenges, and I will let you all design the architecture, and I'll guide you through it. It'll be a wonderful, wonderful, wonderful learning experience for you all. So I'm going to invite you to that completely free to get you guys nothing else other than cloud hired for that solution architect, cloud architect job, or enterprise architect job. So you now know about all the free things that we're doing right now. You've seen the links to sign up for all these things. They're in the description below. But of course, Chris from my team or Leo from my team or one of my amazing, amazing helpers from my team will list these things. So without further ado, let's talk about cloud computing and cloud architecture things. But before we do, if you can put a hashtag cloud hired and a hashtag cloud architect. Could love to see a bunch of them, and that way I know you're here, you're excited, you're ready to go. So hashtag cloud architect and hashtag cloud hired. And after I see some of these, so I know that you're here, you're awake, you're alert, you're oriented, you're paying attention, then we'll get started because I want this to be a wonderful experience for all of you. Raphael and Sandy and Faz, fantastic. This is the way I like to start it. I love seeing all you guys from all over the world, from the Netherlands, who I see over there, to Australia with Precious, to Derek, who's over there in California. Chow, I'm not sure where she's at, but she's absolutely amazing. Z's in that Middle Atlantic region, that Virginia region or Maryland region. We love Z. He's fantastic. And please hit that like button, subscribe, hit the bell, all those things. I'm going to learn how to be a YouTube person. Thank you so much. Cloud Architect, I love it. Cloud Architects, I see it from coming everywhere. Cloud Architects. And why are we training cloud architecture? To get cloud architect jobs or solution architect jobs. There's no point in doing a certification if it doesn't get you there. It was so nice having you on the webinar today with Grit Daily. And it was also nice being seen in Grit Daily. Thank you so much, KF Lou. So thrilled to have you here. So let's start talking about cloud stuff. What are we going to begin with today? We're going to begin with some basic networking concepts. Now, we're going to be doing a lot more networking with you guys in the next couple of weeks because the network is the heart of the cloud. It's like the circulatory system in the heart of the body. The heart doesn't work. Guess what? Nothing works because it pumps blood to the body. The veins and the arteries, you know what they are? They're the network that make us live. So the network is everything. So let's start talking about some networking. So we're going to begin with a basic networking review. And I'm going to start with something very academic called the OSI model. Now, I'm generally not Mr. Theory. I'm all about how to design and build and hands-on pragmatic, hands-on practical. But there are some models that we just have to use, and I'll tell you why we use them. So when we're dealing with networking or communication systems, it's very challenging because there's a lot that goes into it. And when we're trying to troubleshoot or we're trying to design a system, we must be systematic in the way we're doing it. And in order to be systematic, you have to have a logical structure. So the Open Systems Interconnect model, or the OSI model, was developed a very long time ago. And it was designed for networking people like me to be able to communicate with other networking people. The reason it was is if we had a common lexicon or language, we'd be able to communicate accurately. In medicine, we have our own language. In architecture, we have our own language too. And in networking, we have our own language. So they came up with this 7-layer model. Now, each layer contributes to a different part of the network. And if you know these layers well, it will help you troubleshoot things. So I'm going to talk about the 7 layers of the OSI model. Layer 1 is the physical layer. You know what the physical layer is? It's this. Let me just get this cable. This is the physical layer. It's a wire. Physical layer. Here we go. Physical layer. Now, what happens? We send on a wire. We send electrons. Now, if this wire happened to be a piece of fiber optic cable, we'd be sending photons. So what is layer 1? It's physical layer, a wire. So when you're buying a direct connection, if you're not getting link light on your switch or your router, guess what? Layer 1 is down. Layer 1 is down. The wire's not plugged in. Unplug a cable from your computer and poof, you'll see the color change. That's physical layer problem, or the wire. Now the next layer up is something called the data link layer. Now let's talk about the data link layer. If the physical layer is the wire, the data link layer is the logical layer 2 part. It's the network card. So in the back of your computer, you've got an Ethernet card that plugs into your network. That's layer 2. You may have a Wi-Fi card that also has a MAC address. That's layer 2. You may have a plain old-fashioned Ethernet switch, and each one of these ports on an Ethernet switch is layer 2. And what are we dealing with layer 2? We are dealing with hardware or physical addresses, such as a MAC address or a Delcion frame relay, for example. Layer 2 address. So layer 1, wire. Layer 2, physical network piece, meaning like the card. And that's called the data link layer. So layer 1, we're transmitting bits, but they're going to be in the form of photons or electrons, whether it's fiber optic or wires. Now, layer 2, that data link layer, the Ethernet card, we're basically dealing with hardware addresses and called a MAC address. And what we send at layer 2 is a frame. Bits at layer 1, frames at layer 2. Now, layer 3, this is where the party starts. This is where network people like me dance around, and we love it. This is the network piece, is the logical piece where you put an IP address on it. Your subnets, layer 3, your IP address, layer 3, the network address. So in the back of your computer, if you want to put an IP address on it, you go to your card and you manually type 192.168.1.1, and you put a subnet mask 255.255.255.252, for example, for a 30-bit mask for a WAN link, and poof, you put the address on it. So layer 1, physical, real cable. Layer 2, Ethernet card or switch. Layer 3, router, IP address, subnet. Now, what do we send at layer 3? Packets. And if you do a ping -t or a continuous ping to the cisco.com website, and after a long period of time, you see drop packets, you see packet loss, that's what happened. You're losing a layer 3 message. So layer 1, wire, bits. Layer 2, frames, Ethernet card. Layer 3, IP address, packets. Now, the next layer up is called layer 4, or the transport layer. Guess what? This is where your network load balancers work. This is your TCP, your UDP, your ICMP. This is your transmission control protocol, and we're sending segments here. Segments here. That's what we're talking about. So layer 1, wire. Layer 2, MAC address and frames. Layer 3, IP address, subnets. Layer 4, TCP, UDP. Okay, so that's really what we're dealing with networking. Now, anything above this isn't networking. So we network architects like me, we stop here. We go from layer 1 to layer 4, and we're done. That is the world of networking. Now, above that, layer 5, we've got this session thing. And really what we're dealing with, it controls the connections between two users. Typically, it's considered to be data at this point. We're outside of basic networking. And then when we get to layer 6, yes, we networking people do a little bit of stuff here. For example, this is where your encryption is, like your TLS encryption. Again, but we're still dealing with data. And, kind of keep this in mind. When we get to layer 7, or the application layer, think application load balancers. Here is where the user application is. So when I go to my web browser to go to www.cindythecat.com, guess what? I'm at the application layer. And I get pictures of Cindy, my beautiful cat with nice paws, plainy little ears, beautiful whiskers, although I'm not happy about the mouse she brought me 15 minutes ago, but she's my great cat. So layer 1, wire, physical layer, bits. Layer 2, data link layer, frames, MAC addresses. Layer 3, network layer, IP addresses or packets. Layer 4, transport, TCP, UDP. Layer 5, session layer, controls the connection. Think about things like sockets. Layer 6, presentation layer. Think about things like encryption and presentation to the upper layer. Now, layer 7, the application layer. What are we talking about? The user interface, applications, HTTP, HTTPS, DNS, etc. Now you know the OSI model. And why is it so important? Because if I don't have link light, or for example, if I'm on my router and I notice my cable's down, guess what? Cable's down. And I can say I've got a layer 1 problem to the network engineer on the opposite side, and they have to talk about it. If I say we've got a routing problem, everybody knows it's layer 3. And that's why we do it, so we can communicate to each other. A doctor talks to somebody about a macular rash, and they know what it is. We architects and engineers communicate with networking on a layer basis from the OSI model. So now you know. Now, let's talk about in the basic part of the network. To make a network work, or to make any nail delivery system work, you need an address. So I got lots of you really wonderful folks on this call. So right now, I know that Ivo Doikia is Bulgarian, and right now she's living in Hungary. She's one of my amazing cloud architects. So I know that. Now, if I want to send her a letter, I need to know her exact address. Her street name, her street number, an apartment identifier if it exists, the city, the state, the country, and the postal code. And if I know all that, I can send a message to Ivo Doikia saying, thank you so much for all the wonderful things that you do. Now, if I have her address, I can do it. But if I don't have her address, I'm just going to send it out to the ether and it's going to be lost somewhere. Well, in networking, it's the same thing. Every device that has to talk to every device has to have an address. And the address must be unique. So I've got this beautiful cat named Cindy the Cat. I'm sure there's other cats named Cindy the Cat. But if Cindy the Cat lives at 123 Cindy the Cat Street, Palm Beach Gardens, Florida, 33410, Cindy the Cat is there. She's got a physical address. Now, if there's a Cindy the Cat that lives at 127 Main Street in Portsmouth, New Hampshire, that's not Cindy the Cat that lives in Palm Beach Gardens, Florida. And see, that's how we identify them, with postal codes. So in networking, every device that needs to be communicative needs a unique address. And that's why we've got external addresses and internal addresses. We'll talk about that later. But understand this. Every device that needs to be on the network needs a unique address. Because how could I differentiate Cindy the Cat living in Maryland versus the beautiful Cindy the Cat living in Port St. Lucie, Florida? I'd never be able to do it without the zip code. So that's what we're talking about. So with networking, every device needs to have an address, and it needs to be a unique address. So kind of keep that in mind. Let's think a little bit more about that. When we're dealing with IP addresses, we're dealing with IPv4 addresses and IPv6 addresses. For those of you that are old enough to remember, like me, we used to have IPX routing and CLNS routing, and we used to have AppleTalk routing, and all kinds of great routing protocols from our old fun days. But now it's all IPv4 and IPv6. Abigail, I'm so thrilled to see you over there as well, helping out. So thank you very much. So let's talk about IP addressing in your VPC. Well, we're going to be dealing with two kinds of addresses: publicly available addresses and private addresses. So here's what happens. IP addresses, we don't have enough of them. We ran out of them so long ago, it's not even funny. When you're dealing with an IP address, an IPv4 address, there's basically 2 bits to the 32nd. So if you want to know about all the IPv4 addresses in the world, you can do 2 to the 32nd power, and you'll get something like 4 billion. You're going to realize that's not enough to deal with the world's 7 billion people and their smartwatches, their smartphones, their smart refrigerators, their Internet of Things devices, their biomedical devices, all this stuff. We need billions and billions and billions and billions and billions, maybe trillions of IP addresses. And that's why we ran out of IPv4. So what do we do? Well, the Internet Engineering Task Force came up with this concept of the private IP address spacing a long time ago. So 20 some years ago, when I went into networking, I read RFC 19, which specified private addresses. And you know what these private addresses were? The 10.0.0/8 address space, the 172.16.0.0/12, and the 192.168.0.0/16. I'll say it again. The 10/8, 172.16/12, 192.168.0.0/16. They're private addresses. That means they've been specified to run inside of an organization's network, inside of their building. But what are they not? They're not unique. So, inside of an organization, every address needs to be unique. Outside of that organization, guess what? They can't be unique. Outside of the organization, they need to be globally routable, which means a public. So, if you've got a web server or something that's going to be facing the internet, it or the load balancer that pretends to be it must have a public address. All the stuff that you don't want reachable from your internet obviously needs to be firewalled off, and their IDS, IPS systems, your access controllers, your security groups, your host-based firewalls, et cetera, et cetera. You're going to have all that there, but to keep it secure. But guess what? Put a private IP address on it, and it's also not reachable, but you have to do both. So let's talk about these classes. About 1,000 years ago, well, I'm exaggerating the concept, about 40 years ago, like in the late 80s, we had this concept of address classes, and that basically meant no subnetting. And what were these IP address classes? You know, not that it makes any sense now in today's world, because we're using classless IP addresses. There was the class A, which was the 10/8, which is basically the /8, and basically that would give you 16 million addresses on the subnet, almost 17 million. The problem is, if you had two network cards in your computer, and you used a /8 subnet on each card, you would literally be burning 32 million IP addresses for 2 interfaces on your card, on your computer, which wouldn't work. So then they came up with the class B address, which was a /16, which again would give you 65,000 hosts, which is beautiful. But you can't get more than 500 hosts in a subnet because before the subnet gets bogged down with broadcast traffic. So again, not usable until you subnetted it down. Then they came up with the concept of a class C address, which realistically speaking has 254 usable addresses. And then we came up with a class D address, which was used for IP multicast. And by doing that, that's a totally different class. So class A, /8 boundary, class B, /16, class C, /24, class D, multiclass, class E is experimental, and they've never been used for anything. So what does that mean? Nothing in today's world, because we use classless interdomain routing, which means we use subnetting, which means we subnet the class A's down, we subnet the class B's down. If we need a WAN link, we use a /30. If we use a LAN link, we use a /24 or a /23, and pretty much that's all we're doing in networking. We need to subnet them down. So in modern times, we're not doing any more classful routing. It's all classless. And how does this work? We're dealing with great routers. The routers run routing protocols. Ospf, or intermediate systems to intermediate systems internally. They exchange routes and messages with each other. The routers identify each other. They build a map of the network, and that's how they go. So the routers run routing protocols, kind of like a GPS. So Let's say I wanted to go to my COO's house, Chris. And Chris has a really great cat named Sunny the cat. And my Cindy the cat wants to go visit Chris, Sunny the cat. So I put Cindy the cat in the passenger seat of my car. She's looking out cute out the windows. She's having a good time. And I'm on the way there. Now, I have static routes, which is basically a direct path. And as I'm driving and Cindy's meowing along the way and purring and we're having fun, there's a traffic jam. Guess what? I don't know how to go. I'm lost. I go back home. So why routers run routing protocols is now I want to take Cindy the cat to Chris's house to see Sunny the cat. I'm in my car. I'm listening to reggae music, which is what I'm always listening to because I love reggae music. And while I'm in the car and Cindy the cat's meowing and we're dancing to reggae music, all of a sudden there's a traffic jam. But now I have a routing protocol. My routing protocol in the car is called the GPS, and it says recalculating. And I make a left. I make a right. I make a left. I make a right. Poof, I get rerouted. And now Cindy the cat is sharing the most beautiful tuna steak that I cooked for Cindy the cat and Sunny the cat, and everybody's having a cat party. So that's what we're talking about. We're talking about using routers to build a map of the network. And then what are they building a map of? The subnets, how to go from point A to point B. That's what we're talking about here. So what is subnetting? Subnetting, realistically speaking, is taking an IP subnet block and breaking it down into smaller blocks. That's it. So why? Let's go back to what I previously told you before. Every interface on a router or every interface on your server, which means network card, for the most part, unless it's in a link aggregation group, needs to be on a different subnet. If we use the /8 on an Ethernet card, we'd be done. Now, if we use exactly what we need, we don't waste addresses. So here's an example. We take a basic Class C address, a 192.168.1.0/24. We sub that down into a 192.168.1.0/28, a 192.168.1.16/28, a 192.168.1.32/28, a 192.168.1.48/28, a 192.168.1.64/28, etc., etc. We're just using binary math to do this. And by doing this, we're breaking something big. So let me give you another mathematical example. And when we're talking about subnetting, we have to talk about the way that AWS broke normal subnetting, and most of the cloud providers do it too. So it's not just exclusive to AWS. When you're dealing with your subnetting, you really need to calculate how many usable addresses you get. So in a normal world, the formula is 2 to the x minus 2. So if we had a /28 normally, basically it would be 2 to the 4th, which gives us 16 minus 2 to give us our usable addresses. So if we are in the data center or any other network, we will have 14 usable addresses. And here's why we only get 14 and not 16. If we deal with this first subnet over here, the 192.168.1.0, that 0, I don't know sure how that happened. That 0 is the network address. Then we have the 192.168.1.1, 1.2, 1.3, 1.4, 1.5, 1.6, all the way to 1.15. And on this subnet, if someone sends a message to 192.168.1.15 with the /28, it sends a message to everybody. It's called the broadcast. Everybody has to look at it. So we can't use the 1.0 address. Why? Because it's used by the router for the subnet. And we can't use the 1.15 because it's used for broadcast. So what this realistically means that we're doing is we are chopping the network into multiple networks. So we can't use the 0 and we can't lose the broadcast. So we lose 2. So realistically speaking, in networking, if we had a /28, we would have 14 IP addresses. But Amazon does things a little differently. They reserve the first one for the router, just like everybody else. They reserve the last one for the broadcast, just like AWS. But Amazon reserves the first 3 addresses for experimental purposes, and they don't tell us what it's for. So when you're dealing with AWS and your subnets, you always lose 5 IP addresses per subnet, 5. So if you think a /28 is going to give you 14 addresses, and the reality is you only have 11. And if you have your systems up in an auto-scaling group in front of your load balancers, etc., and your system's auto-scale, and you only have 11 addresses but need more, the systems will stop auto-scaling. So your subnet design needs to be perfect. If your subnet design is wrong, you will have a nightmare. If your subnet design is wrong, it will mess up your routing. In 25 years of networking, I will tell you that 50% of all outages I've seen was when someone knew subnetting so poorly that they thought they could just use the subnet calculator, didn't understand how the subnetting worked, used the wrong addressing scheme, and if your addresses are wrong, your routing is wrong because you won't be able to summarize, traffic engineer your traffic. And when people do this, they cause such problems. So whoever does the IP addressing can't be your DevOps engineer, it can't be your SysOps engineer, it can't be a regular cloud engineer. It needs to be the most senior network engineer or network architect you have, because get that IP addressing wrong, I promise you 20 years of problems. Get that IP addressing right, and I promise you do the rest right, you're going to be smooth sailing. And these outages aren't minor outages when your addresses are wrong. These are catastrophic outages. They're billion-dollar outages, the things that make companies go bankrupt. So if you're not familiar with this, get the help of someone who is. And we're dealing with all classless addresses because classful has been done for about 20 years. And in those days, we even had, and the last classful routing protocols I ever even touched were Eigrp, which I never used because it was not anywhere close to anything that was better. And Vpv6 was classless or classful. But other than that, everything's been classless forever. Ospf, Eigrp, intermediate systems to intermediate systems, Bgp, and everything else that we use. So keep that in the back of your mind. Now, remember I said that route subnetting is taking big networks and breaking them down. And I also told you if your IP addressing scheme was wrong, you'd have very messed up routing. And here's the reason why. What happens is routers are computers, sort of. They've got CPUs in them, they've got memory. Some of them even have hard drives, not all, but some do. The rest are flash. And when these systems come up, they run routing protocols. And what happens is, depending upon the amount of links and routes that you have in your routing table, it can fill up the router's memory. And what happens is the router's memory gets filled up. They build this big database of routes coming from anywhere. And then a route calculation changes, and the CPU has to process it, and the routers crash. So I've seen more massive outages in my career from someone that didn't know subnetting and supernetting. And basically, I re-IP addressed the systems, tuned the routing, and companies went from massive outages to never having problems because this stuff is really, really critical. So what is supernetting? It's the exact opposite of subnetting. And why would we do this? To minimize the overhead on the routers. I encourage you to think about it this way. If I connect to 10 different internet service providers, which I do a lot when I design an internet service providers network, they peer to 10 and 20 and 30 internet service providers. When you want to connect to 2 internet service providers to get good internet routing, you have to take full routing tables from the internet. The internet routing table is 800,000 routes. So if I connect to 10 different service providers, I'm taking in 800,000 routes, which are all different from each one. Now, ultimately, each one will have a route to everything else via BGP, but they're going to have different AS paths, different weights, different local preferences, different origin codes, whatever we've done, the way we've set up our tuning. So we know how to traffic engineer our traffic. And all of that is done by route leaking specific routes or route summarization. We need to do this. So summarization is the exact opposite of subnetting. Now let's think about this. If anybody would have thought, how many IP addresses that AWS actually lets you, or how many routes AWS lets you send? Can you send AWS 8 million routes? No. Can you send 100,000 routes to AWS? No. Can you send 50,000 routes to AWS? No. Can you send 10,000 routes to AWS? No. Guess what you can do? You can send 100 routes to AWS. 100. Now, the networks I work on have 40 and 50,000 subnets. Easy. So you can send 100 routes to them. What is 100 routes? 0. Nothing. It's so trivial. I hit more than 100 routes and routers in 1990. It's nothing. But it's not that AWS isn't great. Here's the thing. They've got millions of customers. How would you take 100,000 routes from 10 million customers? You couldn't. You couldn't build a router big enough to do it. So when you're virtualizing your infrastructure and you're dealing with virtual infrastructure and you're dealing with virtual everything, you've got to be smart on how you do it, because they've got millions of people's customers. So they only let you send 100. So when we deal with this, being only able to send 100 routes to AWS, it brings our networking back to 1985 networking. And that's what we're dealing with the cloud, 1985 networking technology. So kind of keep that in the back of your mind. So what do? We summarize the routes. And what does that look like? Let me show you. Let's take these subnets that we created. Let's take these subnets. 192.168.0.0/24, 1.0/24, 2.0/24, and 3.0/24. These are for Class C networks, or /24s, technically, in the CIDR world. And each one has basically 254 usable addresses. So for them, we've got 1,000 addresses, and we have 4 routes to send to AWS. Wait, AWS can only handle 100, not 4. They can only deal with 100. Can I afford to burn 4 of them here? Probably not. But I could take my 192.168.0, 1, 2, and 3. I can supernet them back to 192.168.0.0/22 instead of 4/24s. And guess what? I can inject or advertise simply the subnet 192.168.0.0/22 into BGP, advertise it out, send that one route to AWS. And guess what? It'll come right back to me. So that's why we're doing it. Route summarization definitely is about taking multiple small routes and creating one big one to reduce the routing in the table. There are times where you can take thousands. If your IP addressing scheme is good, you can take thousands of routes and summarize them as 1 or 2 routes. If your IP addressing scheme is bad, you won't be able to do any of this, and you'll have thousands and millions of routes in your routing table if you're not careful. Especially if you've got, a huge number of /30 WAN links and a bunch of /32 loopback addresses. You could have so many subnets so fast you won't even realize what'll hit you. So that's what we're doing over here. Now, while we're at it, let's talk about IPv6 addresses. So I told you we had a problem with 2 to the 32nd. It's just not enough. And that's how many addresses we have with IPv4. So IP4, the reason it's 2 to the second is it's 0 or 1. It's binary. So 2 to the 32nd minus 2. Now you know the usable addresses. Now, because we ran out of IPv4 addresses, the Internet Engineering Task Force said, we're going to do it right this time. We're not going to use a 32-bit binary address. We're going to use a 128-bit hexadecimal address. So if any of you guys are not familiar with hexadecimal math, where binary is 0, 1, hexadecimal is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, alpha, Bravo, Charlie, Delta, X-ray, Echo, and then Foxtrot. So we go from 0 to F. So now we're dealing with 16 addresses. So at 16 to the 120th power, we can use a lot more than 2 to the 32nd power. So we have so many IP addresses with IPv8, IPv6 will probably never run out of them, or at least not in my lifetime, thankfully. So this is good news because I don't have to learn IPv version 8 this way. But I'm sure at some point we'll have so many network-enabled devices that'll be in IP version 8. So just kind of keep that in the back of your mind. So we did a brief discussion of some IP things, and now we're going to get into the VPC stuff, the really cool, fun stuff. But before we do, like anything else, I always want to make sure we ask questions and answer questions. So I'm going to ask Chris from my team to aggregate everybody's questions and bring some for me so I can answer them.
All right. So I'm going to bring in the most recent question first because I think it's the most important.
Sounds good. And of course, get well, Abigail. Dragonfly, can I go over subnetting again? Well, yes, but here's the question. Should we do a 2 or 3 hour subnetting webinar early next week, one night, and really go over subnetting, really good for you guys? Would you guys like that? Because I think it's going to take a little more than 10 minutes to teach subnetting. I'm happy to teach it. I think it's such a critical skill. But I don't think we can do it in 15 minutes. But if I'm going to ask you, say yes. If you want me to do a 2 to 3 hour subnetting workshop one day next week, I will do it. Okay, so the answer is yes. We're going to go over subnetting again. I will make it a 2 to 3 hour special event, and we'll go over subnetting because it matters that much. I hope that satisfied that question, because I want to make sure everybody gets this.
And that's where I thought we were going to go with that. That's why I brought it up.
Okay. Well, when we're dealing with something that can't easily be explained in 10 minutes unless you have a background, let's give everybody the 3 hours it takes to really get them strong.
Yep. All right. So now let me...
While you're doing that, if you can hit the like button, comment, subscribe, hit the bell. We're obviously looking to expand the reach that we have to help as many people as possible. So please, if you're not a member, like, comment, subscribe, that kind of thing. Dragonfly. Does subnetting being breaking addresses into smaller addresses? It involves breaking networks into smaller networks. So similar, but a little different. But it's a great question. It's absolutely critical to know the difference between classless and classful routing protocols, but there haven't been any classful routing protocols in over a decade. I mean, classful routing protocols, so they don't even exist. So all network engineers have been using classless routing protocols such as Ospf, Eigrp, and intermediate systems forever. The last time I saw classful IP addressing was 1999. So, and I haven't used a classful routing protocol since 1998, and the only reason I used the classful routing protocol in 1998 is I had to use it on my Cisco Certified Internet Expert exam. They mandated it, and what they were trying to do is they wanted us to use some auto summarization, some classful things to intentionally break our networks and cause loops. But no, there aren't any classful routing protocols anymore anyway, so we're all dealing with classless. Chris, if you want to bring in the next one. George. Is route summarization the same as supernetting? Technically, no, but yes. So, George, it's a great question. Supernetting is taking let's say you have 2/28s, and they don't have enough IP addresses, and you just make 2/28, you turn it into a /27. That's supernetting. Now, route summarization is where you take the routes in your routing table and you supernet them together, and then you send the route as a single supernet. So it's very, very, very similar, but it's technically a little bit different. Now good. Does AWS impose rules for how to do proper routing and subnetting? AWS has a little bit of rules. It is so basic. And if you don't plan your subnetting ahead of time and you just use the defaults, you will have problems. You need somebody senior to do your IP subnetting design. This is not your cloud architect with 2 years of experience that can do your subnetting. This is not a DevOps engineer's job. This is not a sysops engineer's job. This is a CCIE level job to be the one designing the IP subnetting. I mean, and honestly, most CCIEs don't even have the experience to do it. You really want the CCIEs with 20 years experience, because if your IP addressing plan is wrong, it's everything. So the IP addressing architecture is the most critical thing to any design of anything. It's also the most complicated, even though it seems to be the most easy. And that's where we see most of the problems, where the Linux guy or girl is the one that's doing the subnetting plan, and they didn't really have the complexities. It's that important to get this right. For example, if you were going to design a city, and when you design the city, if you didn't plan the streets out right, the roads out right, and the downtown out right, the plumbing, the sewage, it's never going to work right. We've all been to cities with cobblestone roads where it's hard to go through. We've all been in cities where the streets are this narrow and you can't drive a car there. It's because they didn't plan what was coming. So we're dealing with really important network design here. So kind of keep that in the back of your mind. They do have some rules. You must use Bgp, you must use this, but it's not enough to really plan. You've got to have some knowledge on your end. It's a really great question. Chris, do you want to bring in the next one? Which is more efficient, NAT or IPv6? It's always more efficient to speak to someone in their own language than it is to translate. So if I speak to someone in Greek and I speak Greek, it's great. But if I translate Greek to English, guess what? It's not as accurate. So it's always better and more efficient to not have to use NAT. NAT will add latency. NAT adds a lot of things, and it makes things not really reachable. So it depends on the use case. Sometimes NAT is better if you're trying to hide something, and sometimes NAT is is the worst thing in the world if you want something to be reachable. So it's about knowing which one to use at the right time. Great question. Excellent. In a VP, can we try? Okay, I don't completely understand your question, but I will tell you if everything's in a single router and it's directly connected, like in your VPC, yeah, routing between subnets is generally easy. But when things are not directly connected, you need a routing protocol. Chris, I want to go to the next one. Yeah, that's exactly the key. If your IP addressing is wrong and your subnets are not contiguous, you'll black hole traffic and you won't be able to route summarize. So here's this. If your addressing is wrong, you can't summarize. That's the problem. That's why you need to have your best network architects doing your route summarization. Because it doesn't have to be contiguous. But if it isn't, and your stuff is put somewhere else, that traffic will be lost. Now, if you don't own that traffic, it might be okay. But it depends on the exact critical nature of the traffic, what you want and what you want reachable. So route summarization is about how you do the layout. Chris, bring in the next one.
And this one is equally as important as all the rest of them.
Yes, Tech with Mufaz. Chris, can we bring in a picture of my beautiful cat, Cindy, so the world can see Cindy?
You've been talking about Cindy and Sunny, so I figured that we could share them with their favorite new book.
Yes, let's do that. Okay, here you go. This beautiful little gray buddy over here, that's my beautiful cat, Cindy. She sleeps on my head or my chest or in between my knees each night. Now, this is Chris's wonderful cat, Sunny. And we were talking about them. You should see them. Aren't they beautiful, everybody? Let's give a round of applause for Sunny and Cindy the cat. Cindy puts up with a whole lot for me, although she did bring me a mouse 15 minutes ago, and I have to get rid of that mouse before my wife gets home, but I'm letting the cat play with the mouse because she looked very happy with it.
Yeah, so yes, so this is everybody, this is Cindy and Sunny's new favorite book. Make sure you get a copy also. I'll put the link in the chat box.
And let me tell you, Cindy's an impressive cloud architect. Let me tell you the things she does during the day. She chews through Ethernet cables. She unplugs my OpenCloud Ansible cloud. She uses her Pyros to power off my servers. She pulls out power cables. She eats through Ethernet switches. I mean, she is a really good network engineer and a cloud architect. She's very helpful when I write books and documentation. She walks on my keyboard and injects lots of spelling errors and things like that. So I guess we had to have a little fun for 2 minutes. That's my big helper in the office, Cindy the cat. Oh, Jeannie, I'm so happy to see you here. So now you know about all the cats that go on around here. One day for fun, Chris and I will stream what my house looks like. We'll take you to the garage with the firewalls. We'll walk you through my redundant cabling and show you the network switches and devices, everything. But anyway, let's get back to the content. So if you haven't hit the like button, comment out a surprise, please smash that like button, comment, forward to somebody else. Let's get everybody trained to be great cloud architects. Now let's go back to AWS and let's talk about the VPC. Now, most people would tell you that your VPC is a virtual private network, but that's insane. The VPC is a virtual private network is this, keeping your IP traffic segregated from somebody else or your layer 2 traffic. Your VPC is your virtual private data center. It's where you put your stuff, where you put your load balancers, your firewalls, your servers, your VPN concentrators. They're all in your VPC. So your VPC is your virtual private data center. That's it. It's a data center. When we strip out all the mysticism created by the marketing folks, the cloud is just a data center, nothing else. So what are the components of your VPC? Routing. Routers that connect to the internet called internet gateways. NAT devices. Elastic IP addresses, which are public IP addresses. Endpoints, and we'll talk about that. We'll talk about ways to connect different organizations through VPC Peering. We'll talk about access control lists, and we'll talk about security groups. And this is the fun stuff. The fun stuff. So now that you know that, let's talk about routing tables. So the route or the routing table is like the GPS that I'm going to use to drive me and Cindy over to see Sunny the cat, and I'm going to cook them all tuna because I'm an expert chef. I love to cook, and my cat only eats tuna, shrimp, and scallops, so I'm going to go cook them all some shrimp. So I'm in my car, I'm driving over there, we're having a party, and my GPS is there. Now, inside of my GPS, I have a map. And inside of our tech, we have a map of the network, and it's called a routing table. And here's what it's going to look like. For example, you're going to have a route to a local subnet, and it's going to say local, and that means it's directly connected. On a router, it would say D or C, meaning directly connected. Actually, it'd say C, because D was Eigrp and DEX was Eigrp external. So it'll say local. Now, look over here. You've got a route to this class C network or class B network, because it's got a /16, and you can see where it's going. You can also see you've got a 192.168.1.0/24 going somewhere else. And for this route, the router will choose this path if it parts to this path. And why? Because it's more specific than this. This subnet includes 192.168.0 all the way through 254. This one only here is 192.168.1.0/24, so it's more specific. So that's what you're kind of dealing with. And lastly, we have the 0.0.0 route, which is the default route, which says, if you don't know where to go here. And that's how it works. So how do we routers build up these? How do the routers make these things? Well, here's what your typical routing looks like. There's two kinds of routing protocols. We've got interior gateway protocols and something called exterior gateway protocols. Interior gateway protocols are what we use inside of our organization, and they're designed to be fast, performant, and efficient. So in this case, we're using Ospf. And here's what these routers do. Hello, 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 hello. Every 10 seconds, they send hello to each other. It's like a keep alive to make sure they know it's a health check. Hello, hello, hello. And guess what? If, for example, one of the responders doesn't respond to the health check and says, hello, 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 and on that fourth hello, no, the router doesn't get a response back. The router says dead, removes the link, and recalculates the route for everybody. So why are we using routing protocols? They're self-healing. By using the right network and the right routing protocol, we get a cable cut, it heals itself. You know, like AWS likes to call it event-driven stuff. We've been doing event-driven stuff at Cisco since the 1980s. It heals. So that's what these routing protocols do, and they're amazing. So inside of our organizations, we run an interior gateway protocol. In today's world, there's only two, which is Ospf and intermediate systems to intermediate systems. There's still that great Cisco proprietary Eigrp, but nobody uses it anymore. Why? Because it's vendor proprietary, which means you've got to be on Cisco. And while I love Cisco, while I spent a decade at Cisco, I still believe Cisco is and always will be the best technology company. It's not fair for your customers to lock them into something proprietary, whether it be a DynamoDB, whether it be an Elastic Compute Service, whether it be an Elastic Container Service, or any of those proprietary things. It's not right to lock your customer into something or they can't leave. So Ospf and our intermediate systems are used as intermediate systems is currently used as an interior gateway protocol. And in between organizations, you use an exterior gateway protocol like BGP. So that's the way these things work. What we're actually doing is as follows. We're doing the following. We are setting up our environments. We're using IGP for fast, performant routing inside of our networks, and an exterior gateway protocol called BGP. So when we connect to AWS, why are we using BGP? Because they are an external entity to us. So we're not looking for these much extreme performance. What we're looking for is the functionality. So keep that in mind. So when you're using a direct connection, you're using BGP. When you want to peer with other organizations, guess what? You're using BGP. When you want to connect to 10 different internet service providers, you're using BGP. So BGP is everywhere. And it's my favorite routing protocol. And I spent 10,000 hours on it my first year, 5 years of networking. And I spent a whole career on BGP. So love BGP. So let's talk about BGP. It's an exterior routing protocol. And it's designed to be highly scalable. And let's do the following. Chris, while we're talking about BGP, could you put the document that we wrote on Intro to BGP and put it here so everybody can see it? And could you put out my BGP video? And if the group wants, again, I'm happy to do it. I will make a 3-hour breakout session and teach you all BGP for cloud architects. I'm happy to make a breakout session if we get enough people that want it. And I will teach BGP in depth because you can't be a cloud architect without BGP. And what we can cover in a certified solution architect, associate, or professional, or even an advanced AWS advanced networking, which is like this, compared to what we really need to talk about, which is like this. So if you guys want a BGP special day, type BGP, and I'll do a special BGP day. Chris and I will put it together for you guys if you want that. So going back to that, we'll put together another live stream. But let's talk about what we can right now. AWS uses BGP. When you use direct connection, you can use it with the VPN, and you're going to use it for your VPC peering. And when we start talking about things like cloud hubs and transit gateways and all that cool fun stuff, it's all BGP. In fact, it's the same BGP from 30 years ago that's all brand new services. So if you learn BGP once, there's nothing for you to learn for the future. So all cloud architects should know BGP. So let's talk about it. So super scalable routing protocol. So I connect to 10 different service providers. I'm connecting 800,000 routes from each. So my routers may have 10 million routes in them. That's how scalable BGP is. Now BGP, very tunable. The reason we use BGP is I can create a policy with it. Accept these routes, not these routes. Share these routes, not these routes. Prefer this path, no prefer that path. Take in this information and don't share it with anybody else. We can do so much cool stuff with BGP. BGP has what we call nerd knobs because we like to tune them, and it's really fun. When I'm not a CEO, seriously for real, and I'm not teaching people and speaking to recruiters and speaking to hiring managers and speaking to the press, I'm playing with BGP. I'm a BGP geek at heart. I love it. I've played with it forever. So this is fun stuff. Now BGP is a TCP-based routing protocol. It's not like the rest. It's TCP, which means you need to know this. You need to know that BGP runs on TCP port 179. TCP port 179. BGP is TCP port 179. And why do you need to know it? First, it's going to be a test question, but chances are you may have a firewall in between your routers that are peering. And guess what? If TCP port 179 is not up, you know what's going to happen? The session won't come up. You'll have no routes. Your network will be dead. So here we go. We're going to make sure we give you what you need to. So there's that. So BGP enables an organization to connect to multiple internet service providers. Why? If you had a default route to AT&T and you had a default route to Verizon, and these are my two WAN links to the internet service providers, and they're both 0.0.0, where do we go? I don't know. So with one, we can use one link with a default route, but when we've got two, we've got to get smart. So what do? Okay, if we connect to AT&T and Verizon, AT&T on this arm is a little better for reaching certain things, and Verizon's better at reaching these things. So by having two things and taking in full routes, we use this one and this one and this one and this one, and we're load sharing. That's what we need to do. So with BGP, we're connecting our autonomous system, which is basically our entity, to another entity, which is going to be referred to as an external autonomous system. So if your autonomous system number is the same as the one you're peering with, that's interior or internal BGP. If this is 65312 and this is 65313, and they're different numbers, they're different entities, that's external BGP. So kind of keep that in the back of your mind. BGP is a phenomenal routing protocol. There are not that many of us that truly know BGP well. Again, this is a place to speak to your network professionals, because if you get this wrong, you'll break it. People, when you have someone that's a jack of all trades that's doing things like networking and they don't understand it, you have the Facebook outages that cost $8 billion when somebody makes a BGP misconfiguration. So if you know what you're doing, you won't configure it. These things aren't typos. Routers don't for the most part, don't let you just type in useless nonsense. They complete words or they reject it. So when you see these BGP misconfiguration things, it's because somebody doesn't know what they're doing. And that's the problem. So make sure what you're doing is knowing what you're doing before you do anything. One of those 10 things that hiring managers want is they want someone that's safe, someone that knows what they know and knows what they don't know. Guess what? If you don't know, ask someone and you'll be better off. I'm an architect for 25 years. I don't ever design any architecture where I don't ask at least 10 people. Never. I will bring in the best security guy or girl I know, the best IAM person that I know, the best database person I know, the best big data person I know. I'll bring in the best team of architects from all over the world. And that's what I share with my customers, what we all collaborate on. Architecture is a team sport. So if you're connecting to AWS with a direct connection, it is required to use BGP. Now, AWS supports, there's a common BGP community called No Export. And basically what that means is, what it means is if I'm taking your routes and I don't export them to someone else won't be able to reach you through me. So what does that really look like? I'll show you real quick. Bear with me a second. Because while we're at it, we'll take a minute to describe transitive routing and non-transitive routing and what it really means, since we're talking about BGP. So normally speaking, if this is me, and this is Mike's data center, and it's my own autonomous system. And over here, we have Eva Doike's data center. I'm just going to type her as EVO over here. I know that's not a real name, but she knows me real well. She's not going to yell at me. She's really good friends with Abigail Marks. So we're going to put Abigail over here. Okay, 3 great data centers, 2 perfect people. So let's say over here, let's say that what I'm using over here is the 10.0/8 address space. Let's say what I'm using over here is the 172.16.0.0/16 address space. And over here, I've got the 168.1.0/24. So what happens is if I tell Evo about my route, and then Evo tells Abigail, hey, to reach 10.8.8, go through me. And Evo advertises that route. And then Abigail over here tells her buddy, Abigail, I'm going to have you, you're going to be friends with Leo for the day. So the Leo data, so we're going to have Leo over here. And Leo's data center happens to be 172.17.0.0/16. Now, that affects our route summarization, but these are different entities. So let's say we do this. Now, Leo says, I want to reach Mike's data center. Now, because I shared the information with Evo, who shared it to Abigail, who shared it to Leo, Leo and anybody that's connected to Leo that wants to reach me is going to go through them. Now, is that good? Well, it could be. If I want Abigail and Evo to be transit to me, great. But what if Evo's over there in Hungary, and she's over there and she's got a 1 meg internet connection or even a 1 gig internet connection, and Leo wants to send 10 gigs of data through me? Well, Leo's going to send 10 gigs of data to Abigail, and she's going to send 10 gigs to Evo, who can't have the capacity for 10 gigs. And realistically, what's going on is Evo's taken down. All the internet's traffic went through her to get to me, and she became a transit autonomous system. So AWS supports what's by default gives you mostly non-transitive routing, which means if you send the information to Evo, Evo won't tell Abigail. And by Evo not telling Abigail, Abigail has no idea how to reach me. So what is that? That's not exporting the routes. So non-transitive routing is when you don't send the routes to the next people. Abigail doesn't know how to reach Mike's data center, and Mike's data center doesn't know how to reach Abigail. And that's what we're talking about versus transitive versus non-transitive routing. If Abigail tells, or if Evo tells Abigail about her subnets, and Abigail tells Evo about her subnets, and Evo tells me about Abigail's subnets, I'm going to go reach Abigail through Evo. So, this could be great, and keep that in the back of your mind. So now you know the basic intro, but you want to do BGP, I'll make you that 3-hour BGP thing. First, we'll do the subnetting webinar, and then we'll do the BGP thing, and we're going to do that so you know in the subnets, and then we get to the BGP thing, we're going to do advertisements and all kinds of stuff. Yes, I see an Eigrp. I don't know of anybody that's used that for about 20 years now. Even at Cisco, for the most part, we stopped using it about 15 years ago. The customers didn't want anything that was not open standards, but it was a great routing protocol in its time. And Victor, nobody's information is compromised because of BGP. BGP determines whether the traffic can go from point A to point B. Now, it's either reachable or not reachable. Now, if you hack somebody's systems and they're not working right, you can get there, but BGP does not enable you to break into things unless you have routes that you're not supposed to have. And that is more of a routing issue than a BGP issue. It'll happen on BGP, Ospf, intermediate systems to intermediate systems, or any of that stuff. So now let's talk about inner gateways. First, let's design a gateway. What is a gateway? You know what a gateway is? It's a router. So when you look, if you do an ipconfig/all or an ifconfig on your Linux machine or Unix machine, guess what? Here's what you're going to see. You're going to see your Ethernet adapter. Go ahead and do it. ifconfig on if you're in a Linux system, or Windows command ipconfig/all. And Craig, there's no you don't secure BGP. Well, you do and you don't. I can answer that question when the time comes. But it's not really something that needs to be secured, other than authentication and route filtering. It's not like these other things. So there's no data that you're going to compromise from BGP. So a gateway, the default gateway in your computer, is the router that connects to the internet. A gateway is another term for a router. A gateway connects to similar networks. So if you're in AWS and you want to connect your servers to the internet, what do you need? A router that connects to the internet. What is a router that connects to the internet called? Internet gateway. So now we're calling it an internet gateway here, but it's a router that connects to the internet. So guess what? If you're in the data center, it's the same internet gateway. If you're in Azure, well, they do it a little differently, but it's still an internet gateway. Or if you're in Google, you're still using a router that's connecting to the internet. So it's the same thing, which what we're doing, it's the same thing in the data center. So know what an internet gateway is. You always know. So an internet gateway is quite simply just a router that attaches to the internet. How do you create an internet gateway? Well, management console, create one. You attach it to your VPC. You can create a default route which says, hey, if you don't know where to go, send it to the internet. You put a public IP address on your internet, and poof, your systems are reachable from the internet. Wait, I just said this. Your systems are reachable from the internet. Your systems are reachable from the internet. What does that mean, everybody? If your systems are reachable from the internet, what will happen by the end of the day if you're not careful? You will be hacked. So the second you use an internet gateway, you need maximum security, way beyond WAF and Shield. So we'll talk about how to secure these systems later. But no, once you have an internet gateway open, and you've got a public IP address on your load balancer or your server, you are now open season for hacking. So we're going to need a lot of security. So architecturally, what's this look like over here? Basically, we've got our servers. Now, typically, because we've got multiple web servers, we would typically have this. We would typically have a load balancer, which would have a public IP address, and the internet gateway, which takes us to the internet. But it's that 0.0.0 route, which you can see is pointed to the internet gateway over here. That's the route that says when you don't know where to send it, that's where you go. So an internet gateway enables you to go out to the internet and be reachable from the internet. So warning, 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 warning. When you're on the public internet, security, 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 security. If you're not on the public internet, you still need to be concerned about security, but you are much, much, much less at risk. So keep that in the back of your mind. So let's talk about the next kind of internet gateway, but it's different. Egress only internet gateway is what we're going to talk about now. So ingress is inbound, egress is outbound. Ingress is inbound, egress is outbound. So the next type of gateway that we're going to talk about is an egress only internet gateway. Egress only. What does that mean? It means we're able to go out and our traffic can come back, but systems on the internet won't be able to reach us. Egress only. So what is an egress only internet gateway? Well, in AWS terms, for the rest of us, this is just not going to the internet. but with IPv4. But we're in AWS, and egress only internet gateway is basically a gateway that connects your IPv6 systems to the internet. And it only allows them to go out and the return traffic in, but it doesn't allow other people in. So if you want to keep your system firewalled off, blocked inside of your network, you want them to be able to go out to the internet to update operating system patches, etc., and lock your system down, and you don't want anybody coming in, guess what? That's an egress-only internet gateway. Kind of keep that in the back of your mind. So this is beautiful. It doesn't allow inbound, but enables you to go out and come back. That's an egress-only internet gateway. So after that, let's talk about the next type of NAT options you have. And we're going to be dealing with IPv4 one-way access to the internet, egress only. So there's two ways you can do egress only internet for IPv4 and AWS. There's the old way and the no longer recommended approach, which is something called a NAT instance. And what is a NAT instance? It's a virtual machine that performs NAT. So you create a virtual machine. The virtual machine translates your private addresses into your public addresses. And then that NAT instance gets pointed to an internet gateway. And when you use a NAT instance combined with an internet gateway, then what happens is the devices behind the NAT instance can go out to the internet for egress only. And the return traffic's allowed back. But anything behind the NAT instance is not reachable from the internet. So it's partial internet access. But AWS doesn't recommend using NAT instances. So we're not going to talk about them anymore. But here's what it looks like. It looks quite simply like this. Got a bunch of servers. You connect into this little EC2 instance. It's like a little Linux machine that does not. That thing has a default route to the internet, and that's how that works. So these devices can go out to the internet, the traffic can come back, but nobody can go from the internet and reach them because they're behind the NAT instance. So let's talk about NAT gateways. And NAT gateway is how you create egress-only internet access for IPv4. So egress-only internet gateway, IPv6. NAT gateway, identical for IPv4. Fully managed NAT service, which is redundant inside of an availability zone. You put it in your public subnet, and you put an elastic IP on it, which you get for the life of the gateway. You make sure every device has a default route to the NAT gateway, and each AZ should have its own NAT gateway. You do this, devices are talking to each other, and poof, everything is great. So a NAT gateway is a fully managed NAT service. It's functionally the equivalent of an egress-only internet gateway, but that's for IPv6. This is for IPv4. Kind of keep that in the back of your mind. So what's this look like? This looks like this. You've got your systems. This NAT gateway is providing both internet access and NAT in the same device. And there we go. So kind of keep that in the back of your mind. So, Chris, how long has it been since we've taken questions?
About 25 minutes.
Okay, so before we get into elastic network interfaces, let's bring in some questions.
Can you stop sharing your screen?
Yes, thank you. We can say the VPC is equivalent to a virtual private data center, meaning the whole building with all the routers, switches, and firewalls. Where a LAN could basically just be two computers plugged into a switch. So I'd say it's more like a data center than a LAN. Chris, you want to bring in the next one?
I'm having to scroll through all the BGP request. So give me just a second. Here we go.
So Nagaraj, which is a great question. Whether you're using standard IPv4 or whether you're routing on Ethernet over MPLS, you're still going to be using BGP. Now, if you're dealing with straight MPLS Nagaraj, you're typically dealing with RSVP signaling and label switching protocols like that. Because what we're doing is we're taking an IP packet, we're sticking a label on them before we inject it, then we're routing them through our network by popping and swapping labels. Then when we get to the last hop, we pop that label and turn it back into an IP packet. So when we do like BGP VPNs, for example, We have an underlying MPLS network with primary and backup explicit paths, which are signaled via RSVP. We're using label switch distribution protocol or tag distribution protocol. We're typically using intermediate systems to intermediate systems in a very flat network, although we could be running a single area OSPF. And then we're going to run BGP on top of that. So point-to-point and MPLS, everything every time we connect to a direct connection, we're definitely going to be using BGP. But you don't have to use point-to-point connections with BGP. Use BGP connections when you're connecting to external organizations like AWS. Inside of your organization, on the point-to-point connections, you're probably using OSPF. Yes, Brad, EIGRP was a routing protocol that Cisco had many years ago. It was an enhancement to IGRP. Nobody uses EIGRP at all in today's world. And for the most part, nobody has for about 15 years. It was a great routing protocol in its day. What happened is the routers didn't have enough CPU performance to run OSPF. So they had this protocol called EIGRP, which had some functionality like OSPF, but not really. And it was a distance vector protocol that built a topology map. And it was very good. But it forced people to use Cisco. And the customers didn't want to only use Cisco. It meant they couldn't use Extreme Networks. It meant they couldn't use Juniper. It locked them in. So EIGRP has been a dead protocol for a very long time. But it was a really great protocol in today. And I did a lot of it. In fact, it's funny. The first paper that I wrote, one of the built my career, the first one was an intro to multicast. And if you go out there and look up my name, you'll see a paper that I wrote about 20 years ago about how to migrate from EIGRP to OSPF. And thousands of people have read that article and done it, because OSPF is like anything else, vendor proprietary, which means you're locked in. And guess what? EIGRP doesn't work well with MPLS, and EIGRP has all kinds of problems, stuck in active states, so it's nowhere close to as good as OSPF. And that's why in modern worlds with routers that have actual memory and CPUs, we don't use that anymore. Now, years ago, it was lightweight and we had to use it, but in today's world, it's just not something we use anymore, except in really small environments. How about CCNP or Devnet? What about it? I don't know what you mean by CNNP. Now, Cisco does have a Devnet cert for people that want to be doing API work, not me. The CCNP is a very good Cisco networking certification for people that want to show competency in networking. Craig Hard, do you secure BGP? Look, BGP is a routing protocol. So, I mean, what are you really securing? You're using MD5 authentication to make sure that, you know, the BGP speaker on one side and the BGP speaker on the other side are who they say they are. Now, that's it. Now, will we determine which routes we inject? If you don't have a route to something, you can't hack it. So yeah, we're going to do that. So we're going to filter routes. We're going to make sure that we don't export routes that we don't, so we don't want to become transit. We're going to tune policies, which effectively is securing organizations. But BGP is not like a web server that you've got to service. It's a routing protocol. That's a good question. Is non-transitive the same as the split horizon rule? No, not even close. So what is split horizon? And split horizon is something that does not come into play in today's world at all. It's only split horizon is only applicable when we're dealing with distance vector routing protocols, which nobody uses anymore. And here's what split horizon was. If, for example, we don't use distance vector protocols for this reason. The way a distance vector protocol is, we have Mike, we have Ivadoikia, and we've got Abigail. We've got Abigail over here. And
we can't see your screen.
Okay, thank you. And this is why we stopped using. This is not where it's supposed to be. I'm sharing the wrong PowerPoint. Bear with me. So let's go back to this slide over here. Okay, so here we've got an environment, and we're using a distance vector protocol because it's 1989. And here's what this is. So I'm Mike. What I do is I tell Evo, hey, guess what? These are the routes that I have, and I learned these routes from somebody else. And Evo says, guess what, Abigail? I can give you my routes, Mike's routes, and the stuff Mike told me about. Okay, have any of you ever played Whisper Down the Lane before in your lives? Where I say something to one person, and they something to something else, and they tell somebody else, and by the time you're done, I said Cindy's a cute cat, and they say Mike is going to buy a lion. and you're like, Cindy's a cute cat, and somehow somebody else thinks Mike's buying lions and tigers and bears. Well, that's distance vectors. All it is routing by rumor. Hey, I heard this, I tell you. And then the other person tells somebody else. So what happens is we're in an environment where we create routing loops because it's inaccurate. But what split horizon would say, if a route comes in this interface, don't export it out that interface, and therefore you don't have a loop. So split horizon would say, if a route comes to me, don't let it advertise it on the same interface. But we don't use distance vector routing protocols anymore because they were so bad. And with regards to loops, it could take you 90 seconds for a cable cut to be noticed. You could be losing your traffic forever. So that's the concept of these EIGRP and IGRPs and RIP stuff, and that's why we don't use them anymore. So split horizon is not the same as non-transitive. It's very similar, but not the same, because the split horizon is only applicable to distance vector routing protocols. So with egress only, you can go pull your updates, but other people won't be able to come in and reach you. Sada, you mentioned there is no transitive routing. Is it possible to build a VM with a software-based routing application and use this VM to create transitive routing between VPCs? Well, Sada, here's the good news. It's not that complicated. So in interior BGP, we don't allow transitive routing, but in exterior BGP, we do. So what did we do in networking many years ago? We came up with concepts of confederations and route reflectors, which basically said, break the rules of non-transitive routing. So all we have to do in the cloud to break the rules of non-transitive routing is just to simply enable the route reflector that we've done with Cisco and Juniper for 30 years or so. So they have some new route reflector technology, brand new innovation called Cloudhub and Transit Gateway, which are those same route reflectors that we were using in Cisco 20 and 30 years ago. And why were we using a route reflector? Because if we learned a route in IBGP, it didn't advertise it to somebody else. So a route reflector says, come in and come out. So a route reflector takes us back to the same transitive routing environment that we were just talking about over here. If we now do Cloudhub, and let's say this is now Cloudhub. Oops, I don't even know how this works. I'm not sure what's going on here. But anyway, so if we're like in this particular environment over here, if this was Cloudhub, let's pretend Ivadeuki became Cloudhub. And now we've got VPC A, and we've got VPC B. Now, in BGP, pretending this was IBGP, C over here would be something called a route reflector. And what would happen is VPC B would send this information to the route reflector, who would send it to VPC A over here. And that's how the two would communicate, because the route reflector breaks the rules of non-transitive. So if this thing isn't a route reflector, the routes are going to go from VPC here to here, and then this won't tell VPC A. So by making it a route reflector, we solve that. Oh, wait. AWS has something called Cloudhub. What's Cloudhub? Connect to these devices via eBGP and allow transit routing. Brand new invention, 2020. Transit Gateway. We allow same route reflector. VPC B sends the information to Transit Gateway, who sends it back to VPC A. And poof, we're done. So what is Cloudhub? What is Transit Gateway? It is a BGP route reflector from 1990. Same concept. And that's why this stuff is great, because it's all old 30 and 40-year technology. When people say, Mike, how do you keep up with the cloud? I'm like, what do you mean keep up with the cloud? The cloud hasn't even gotten past 1980 yet, other than faster. So it's always easy. This is all network and data center stuff. That's why the CCIEs like me get hired with no cloud certifications, because we've been doing cloud stuff since 1990s. And that's why I want you to learn the network, because if you learn the network, you will be always, always, always in charge. The world will come to you, and you're always going to know what to do. So let's talk about next. With regards to next, we're dealing with elastic network interfaces. And elastic network interfaces are virtual network cards. Virtual network cards, and that's it. And virtual network cards. So you got a network card in a computer. Realistically speaking, it's a virtual network card. So if you want to place your systems in a subnet, it needs a network card. Now the default, 1 second, is I'm not sure what that message says. Can you guys see me and hear me?
We were doing questions. So are we still doing questions? Or
no, we went back to the content.
No, we didn't. We didn't have a clear. You went straight from a question into content. So that's.
Oh, were there more questions I didn't know about? Because we can answer
them. That's
okay. Let's do that.
Right.
Can a NAT instance be replaced with a firewall? Now, Kemi, the reality is in a data center, yes, but in the cloud, we still need that connection to the internet. So what we'd have to do is we'd have to use a firewall and connect it to an internet gateway. But yes, then we could do it. But we can't use one firewall in the cloud. We'd have to use 2 firewalls. So we'd put it behind a load balancer. With the BGP Pro, with the BGP protocol, does AWS use it by default, or does one have to specify? You can't connect to AWS with a direct connection without doing so. You have to use it. But if you're going to use Cloudhub or Vpc Pairing, you're also using it. There's nothing to install. It's a routing protocol. It's things that routers do.
And
it's not an application.
Some of these questions we may not have gotten to the content yet. So tell me.
Can you explain the difference between a NAT instance and a NAT gateway? Yes. NAT gateway is a full internet connection and NAT in the same device. NAT instance is a device that just translates one device to another and still requires a NAT gateway. Does a VPN or direct connect need NAT? No, because those things are not going to be NATed. They're connections to the things. NAT is used, well, NAT would be used in a business to translate one address to another. For example, those kinds of things. You had somewhere that a Bastion host is a secure way to NEC. So never, ever, 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 ever use a Bastion host. What a Bastion host is, which is the most crazy thing I've ever seen, is you stick some computer in the middle of the internet, you put 2 network cards in it, you SSH or remote desktop into this thing, and then you go out the back into your private network. By using a Bastion host, you basically get rid of all your firewalls, all your IDS, IPS systems. It bypasses all your security. So the best way to connect remotely is to have a firewall, which with an IDS, IPS system to create a demilitarized zone and only allow IPsec traffic to do it. I would never use a Bastion host. I could hack into pretty much any network in minutes with a Bastion host. It is the perfect way to have your systems get hacked. I know Bastion hosts are taught in certification courses, but those aren't people that are actually working as architects. Use a Bastion host at your own risk. Here's what a Bastion host is. You put someone outside of your house with a big giant sign that says break in. Here's a key. And all they have to do is break into the Bastion host, which is like a simple Windows machine in the middle of the internet, and poof, they've got the key to your house. So Bastion host is something you will never, ever, ever should use. So it's a way to remote access into your network by bypassing all good security. So don't ever use Bastion host. And maybe I should make a video on why nobody should ever use a Bastion host.
Yes, that's a great idea. I like that idea.
And we're going to mention one thing. Nobody can tell you what kind of routing protocols are used by the State Department. If they do, they would be put in prison. And the reason is you've got non-disclosure agreements when you're talking about these big high security environments. So let's keep everybody focused. Let's keep with the architecture, and no, our organizations could not be providing this kind of information. So let's make sure we stay with accurate things, because I want you guys all to become really great cloud architects and have great careers. So let's talk about network cards. The back of your computer has an Ethernet card. The Ethernet card is where you plug in your Ethernet cable, which plugs into your Ethernet switch. And that's how you get attached to the network. So what normally you've got something called network. And it's called the network interface. Now with AWS, how do they brand it? They stick the word elastic in front of everything. So you take a network card, you stick elastic in front of it, and poof, You now have an elastic network interface, which is just basically an Ethernet card sitting in your server. So when you set your systems up, here's the thing. They have a network card. By default, it's ETH0. Anybody work on Linux and Unix systems? Guess what the default system was? ETH0 for the last 30 years. So, that's why it's going to be ETH0. Now, there are times where you would place a system on 2 subnets. One such use case would be a Bastion host, which I'll tell you, please don't ever do unless you choose to be hacked. And the other way would be, let's say you've got a server that supports 2 subnets. So you've got 2 different network cards in there. One has direct performance to one subnet, and maybe you've got a management network where only the people from a certain department can actually access it. So you've got your systems locked down and the such. Kind of keep that in the back of your mind. So let's next talk about public IP addresses. So I told you before that everything on the public internet has to be reachable. Cindy the cat needs her IP address. In addition to Sunny the cat needs her IP address, and all these kind of things. So keep that in the back of your mind. So how do we get a public IP address? Well, normally we call internet service provider, hey, I need an IP address. Okay. And they tell me what it is. But this is a little different. We're not dealing with an internet service provider. We're dealing with AWS, and they've got really cool automated systems. All we do, we want to get a public address. We click on a button, we get an elastic IP address. We are getting an IP address that we pay for from AWS that we can keep as long as we want. So what do you think is going to be on your web servers, or your load balancers, or your internet gateways? A public unique IP address. So that's what we're talking about. So realistically speaking, what's this going to look like architecturally speaking? We've got the internet. We've got a router that connects to the internet. This is called the internet gateway. We have the virtual router in our VPC, and which is doing the routing. We're not going to count that. So let's say you've got a load balancer over here fronting your web servers. The load balancer over here is going to have the public IP address of your website. But it's going to have a route to the internet gateway, and then everything's going to go out. So kind of keep that in the back of your mind. So let's talk about VPC endpoints. What is an endpoint? An endpoint is a way that you can connect one thing to another thing. So AWS has endpoints. All your cloud providers have endpoints. All of them. Your endpoints, the reason you're using are they're going to give you a secure way to do things. So they give you high performance connectivity. They have low latency. They have high security, and they are minimal cost. So that's why organizations use VPC endpoints. So let's talk a little bit more about these endpoints. What's it going to look like? I want to show you 2 ways that we could do communication. So let's say we've got information in our VPC, and we want to stick it in S3. Well, we've got 2 ways we could do it. We could be crazy. We can send our data out to the internet, across the internet, and back in. Now let's think about that. With AWS, we pay to send our traffic out. So we're going to send it to the internet, which is not secure. We're going to send it to the internet, which is the worst performance we have because it's not guaranteed. It's best effort. So we're going to send our stuff to the internet. We're going to pay to send it to the internet. And then, so we're going to pay to send this to the internet, and then we're going to send it across the internet, and then we're going to go back in. So we've got off of our private network, we've got off of our secure network, we've got off of our high performance network, and poof, we're going to then send it over the internet. This is insanity. So what do? We can use the AWS network. Well, is the AWS network higher performance than the internet? Yes. Why? Because AWS controls it. So what if we can go straight from our VPC, hit this endpoint, and then go directly securely into AWS S3, which is what we're going to do. So endpoints are a way for you to take your stuff that's on the AWS network and connect it to the AWS network without traversing the public internet. Remember, internet performance is not guaranteed. Internet performance is slow. And that's what we're really talking about here. So make sure your data goes from your VPC to your S3 bucket in one fell swoop. That's why we're using endpoints. So endpoints are going to be used to connect to a lot of services, and they're very, very, very valuable. So let's talk a little more about endpoints. There's 2 kinds of endpoints in AWS. there's gateway endpoints, and there's interface endpoints. And let's talk about what these are. When you're dealing with it, so we'll first talk about the gateway endpoint. The gateway endpoint is a high-speed endpoint to access AWS services. Here's the way it works. You know how that thing has that virtual router that I showed you with that virtual routing table? When you deal with a gateway endpoint, it places a route to the service in the routing table. And then it uses the private AWS network. So an S3 endpoint enables you private access from your S3 bucket to the S3 bucket to your VP list. So what's going to happen is you create the endpoint, and it's going to create a prefix list, which is kind of like a route list. And you'll see it in the routing table. And that's how you're going to reach it. You'll have a static route to wherever your bucket is, and it's going to look like a PL-SSXXX, and that's what it's going to be, where that XXX is going to be swapped by 123 AB, whatever the name is. So now you've got a gateway endpoint, puts a route on the routing table, and connects you to the routing table. Now, because this is routing, you've got extra security. So Eva Doikio's out there over in Hungary. She's responding to comments. She's writing incredible articles. She's designing phenomenal security architectures. I know her real well. So she's over there doing that. And I want her to reach my data center. I send her a route to my data center. If she doesn't have a route to my data center, she can't reach it. But she needs a route to my data center because she does all kinds of great cloud architectures. So when we're dealing with gateway endpoint security, remember it's a route on the routing table. Let's say I've got a bad, evil cat, the meancat.com. I got a cat that likes to hurt my cat, and she's real mean. So I don't want that cat to know how to find my house or to find my S3 bucket. I don't send the mean cat the route to my routing table. And that mean cat's that way outside, and my cat Cindy's partying and having fun. So I do that. So if you don't send an invite to the party to people you don't want to go to the party, guess what? They don't attend the party. So what is gateway endpoint security? Don't share the route if you don't want anybody to reach it. So keep that in your mind. I don't know why my thing's beeping. I thought I was on mute. But something must have gotten through. So we talked about the gateway endpoint. So what's the next kind of endpoint? It's called an interface endpoint. And an interface endpoint is a way to connect to several AWS services, maybe the EC2 System Manager, Kinesis, the last load balancer, APIs, et cetera, et cetera. So, you know, when you're creating an interface endpoint, it does things a little differently. The interface endpoint basically uses the AWS private link service to connect to the service. And what happens is it basically creates another virtual network interface on your side and the other side, and they're on the same subnet. So when you're creating an interface endpoint, what you're realistically creating is just two network interfaces and a private line between them. And by using an interface endpoint, you can connect to so many AWS services. So interface endpoints use AWS private link. It's a virtual private line over the AWS network. So that means guaranteed speed, performance, and bandwidth. And it's going to keep your traffic, all of it, stuck in that private, secure connection. So guess what? You're not hacked. It's secure. It's not like the internet. That's why we're dealing with these interface endpoints. And those are exactly the reasons. So what's it look like architecturally speaking? I'll show you right now. Here we've got two VPCs over here. This is our main VPC. I'm sorry, this is we've got a VPC endpoint over here, and we've got some private stuff over here. And we're going to be reaching stuff from this VPCs too. So typically what we have is this is what's called like a shared service VPC, where this VPC has services. We are connecting via private line to those services, and then we can receive those services. That's typically what we're talking about over here. So when we're dealing with private link, what are we talking about? Connecting VPCs. Isn't there some other way, Mike, to connect VPCs in the AWS cloud? Yes. But there's two ways you can do it. So to connect to other AWS services or to connect to other AWS VPCs, you can use private link, which coincidentally is an interface endpoint. Or you can use Vpc Peering. So we'll be talking about Vpc Peering as well. So let's continue with the interface endpoint and Vpc Pairing and talk about the differences. To connect multiple VPCs, we use Vpc Peering or private link, but they're different. So Private link, or that interface endpoint, is to connect two exact entities to one service. So if all I want to have is someone reach port 22, then guess what? I'm going to use private link. It will only share port 22 SSH to a single server because I've set it up in private link. By comparison, if I have Mike's data center and Eva Doike's data center, and we're doing VPC pairing, everything she has, I can know about. And everything I have, she knows about until I filter routes or firewall or things like that. So private link is for one service. So if you only want to access one thing, use private link. What if you want to share, what if business A buys business B? Well, if business A buys business B, you need access to more than one service and you need VPC pairing. So keep this in the back of your mind. So if you've got to share multiple services, VPC pairing. If you only want to share one service, private link. So the next thing to consider, VPC peering allows 125 connections. If you think that's a lot, it is absolutely nothing. And I'll show you why it's nothing coming soon when we talk to about full mesh and n times n-1 divided by 2, but we'll get there. So when you're dealing with private link, you've got some really good performance too. In fact, the performance link of private link, for the most part, is limited by the speed and throughput by your load balancers and services. So it is really, really fast. And keep that in your mind. So go back. What's the main difference between private link and VPC pairing? Private link solves the problem when connecting to external organizations. Now, remember we talked about RFC 1918 addresses, and I said every organization internally uses the 10/8, the 172.16/12, or the 192.168. So let's think about this. I have Go Cloud Architects. Then I form a company called Go Cloud Careers. Then we want to share information between them. It's VPC pairing. So kind of keep that in your mind. And by doing this to two companies, but let's say now I have Go Cloud Architects that I found. And let's say somebody else designed Go Cloud Careers, Chris, for example. And let's say that I bought Go Cloud Careers. What kind of IP addresses do you think Chris is using? I can tell you Chris would be using in his cloud the 10.8, so 0/8, the 172.16/12, or the 192.168/16. Why do I know this? Because that's what everybody's using. We're all using private IP addresses internally. So if one company buys another company, do you think you may have overlapping IP addresses? Yes. How do we deal with overlapping IP addresses until we can change the addresses? We use NAT. So when you're using private link, it automatically does NAT to make sure that you and the external entities don't have any problems with IP address conflicts. That's how awesome private link is. I mean, it's awesome. Awesome. So VPC peering would require unique address spaces. So if Eva Doik is running on the 172.16 and I happen to be running on the 172.17 and we're both on /16, we're good. But if we're both using the 172.16/0.0/16, we're going to have overlapping IP addresses, and then we're going to need NAT. So kind of keep that in the back of your mind. So now let's talk about VPC peering, which is what I love. Why do I love VPC peering so much? Well, I've been the BGP guy my whole life. VPC peering's all BGP, so it feels nice, warm, and fuzzy. So VPC peering is a method to connect multiple VPCs. VPC peering provides a non-transitive connection. Effectively speaking, what do I mean by that? I tell Abigail, and Abigail won't tell Eva Doike, and that way we've got security, meaning Abigail doesn't become transit for the whole internet. So that's why we're doing it. When we're dealing with VPC peering, the communication is over the private P space, and in between regions, the traffic is encrypted. Kind of keep that in the back of your mind. So let's look at this over here. Here we've got VPC 1, VPC 2. We're doing VPC sharing between us, and everybody's talking to each other. Wonderful, wonderful, wonderful. Now, we kind of run into these challenges of VPC peering. So VPC peering is not transitive. And I'm going to show you again what that means, which means routes that you learn you won't pass on to somebody else. So you have two options. We get into the Bgp Route Reflector situation, or we fully mesh our peers. And I'm going to show you what we mean by both, fully mesh versus this. Now, fully meshed means everybody's connected to everybody. That doesn't sound like much, but I want you to think about this. We only have 125 Vpc pairing connections, which is not that much. The formula to fully mesh, and I'll show you what that means your peers, is n times n minus 1 divided by 2. Okay, what does this mean? This means if you've got 10 VPCs and you take 10 times 10 minus 1, which is 9, you've got, and divided by 2, if we've got 10 VPCs and we pair them together, we already have used up 45 connections. Now, we only have 125. Now, there's going to be organizations with thousands of VPCs. Easily. You're going to be running pairing between them. So when you start thinking about that and start thinking of fully meshed n times n minus 1 divided by 2, you realize you've got a problem. So keep that in the back of your mind. So this is the, let me show you what this, and let's go back to the transitive routing. Let's say over there, VPC A is me. And let's say VPC B, let's say I'm now an auto manufacturer, and VPC is tires, and VPC C is batteries, and VPC D is hoses, VPC D is windows, VPC F is seatbelts, VPC G is tires, okay? All the elements that go into my car manufacturing. Now in this environment, if I peer with all those people, I can speak to them completely, and I absolutely love it. It's perfect, right? But they can't talk to each other, and here's why. I don't send VPC's routes to VPCC. And if C doesn't know how to reach VPCC, they can't talk to each other. So in this environment, which is perfect, I'm in the center and I can talk to everybody, but they can't talk to each other. Now think about how good this is in this environment. I'm an auto manufacturer. Do I want the tire people talking to the battery people through me? No. I don't want all their business using my network bandwidth and my servers. I don't want that. And my battery people don't need to talk to the tire people, who don't need to talk to the brake people, who don't need to talk to the seatbelt people. So in this environment, running hub and spoke is perfect. But what if VPC B and C needed to talk to each other? Let's say now it's a single company. I am the main company because I founded the company. And Eva Doikia's got some company she's running, and Leo in Brazil's running some South American division, and Alonso's VPCD doing something, and now Chris has got something going on. Now I got to exchange information, and I need them to talk to each other to collaborate. Well, now this doesn't work. So I have to switch to fully meshed, or Cloudhub or transit gateways. So let's go to fully meshed so you can see what that looks like. This is what we mean by fully meshed. Everybody has got a connection to everybody. Now look how simple and elegant this is with 3 of them. Everybody's got a connection to everybody. VPC-C tells VPC its routes, but VPC-C won't tell A, but that's okay because VPC-B tells A. So A knows how to reach B through this link. A knows how to reach C through this link, and C knows how to reach A through this link. So everybody's having a networking party. They're all talking to each other. Life's good. Life's grand. But remember, n times n minus 1 divided by 2. We've only got 3 VPCs here. Now we've got 4 of them. 4 times 4 minus 1, which is 3. So 4 times 3 is 12 divided by 2 is 6. Now I've got 10 of them. 10 times 10 minus 1 or 9. 10 times 9 is 90 divided by 2. You can see this goes up really, really fast, real fast. So it becomes a nightmare really quickly. So keep that in the back of your mind. So what's the workaround to this? Well, in the 80s, we had Bgp Route Reflectors, like the late 80s, early 90s. Here we had a route reflector. So AWS has a brand new modern 1990s route reflector solution, which is perfect, and they call it Cloudhub. Now let's be fair. Cloudhub gives you the flexibility to do what we struggled with iBGP 30 years ago. The networking world made the solution to that called a route reflector, and AWS has very intelligently, like the other cloud providers, taken that same great technology and rebranded it. Now, they could have called it a route reflector, but they called it Cloudhub. So we call it Cloudhub. So what Cloudhub does is it enables you to break the rules of non-transitive routing. That's it. So now it allows your non-transitive routing to work. So it basically says, yes, I want to enable transitive routing, and then it all works. So the way it's going to work is you're basically going to connect to a virtual gateway or a transit gateway with Cloudhub, and each site is going to use eBGP to connect to it, and it's going to look and feel like normal eBGP routing instead of iBGP routing. So here's what it's going to look like. Say we've got users in Boston, users in Washington, users in San Francisco. They all connect via eBGP to this virtual router over here. And Boston, because it's eBGP, will send its routes to Washington and San Francisco. And Washington will send its routes to Boston and San Francisco. And San Francisco will send its routes to Washington and Boston. And poof, everything goes up and absolutely perfect. And that's transitive routing. So without Cloudhub, we've got non-transitive routing. With Cloudhub, we've got transitive routing. But one thing to remember, one really critical thing is Cloudhub only works with VPNs. Now, when we're building systems, VPNs aren't that great. They don't give us the performance we need. So if we need to use direct connection, we're going to need another solution. But let's just talk about it a little more. So remember, the whole point of this is transitive connections without running full mesh. So I'll show you one more way, and then I'm going to compare it to the other AWS service, which to we network architects is the same as Cloudhub. Now, to the people that just know certification but don't know architecture, they're going to think it's different, but they're the same. Functionally, it's all a Bgp Route Reflector. So let me give you one more picture of Cloudhub with the BGP thrown in there. Here, what you can see is we've got BGP over here with one autonomous system, a different autonomous system, and a different autonomous system where we're sharing the subnets and sharing the routing, and everything is great. Now, AWS has a new thing. It's called Transit Gateway. What's the difference between Transit Gateway and Cloudhub? Cloudhub only works with VPNs. Transit Gateway works with private lines. So what's the main difference between the two? VPNs versus private lines. So Transit Gateway is going to give you much better options because you can do private lines, VPNs, etc. It's a more modern version of Cloudhub, but in the end, strip out all the mysticism, demystify the cloud. It's a BGP Route Reflector. Keep that in the back of your mind. Chris, how long have I gone without getting to questions? Because I can go into network ACLs or I can answer some questions.
We need to take some questions.
Okay, let's take some questions. I love taking questions. What was that Radio Shack question? They had this commercial. I loved it. It came out. You've got questions, we have answers. And I used to go build these radios all the time and things with circuits because it was cool. And when they had that question, I used to go in there for answers every single day.
All right, give me just 1 second.
Sure, you got it.
And if they're unrelated or we haven't gotten to them yet, just let me know.
How could you gain access to instances in a Bastion host? Well, I'm going to recommend you never, ever, ever.
It says without using
a
Bastion. Yes.
Okay, so if you've got your VPC, you've got either a direct connection or a VPC connect or a direct connection or a VPN. All you have to do is ride that direct connection and ride the VPN, and you're accessing it from your secure private network, which is protected by your firewalls, your IDS, IPS systems, your access control lists, your security groups, your host-based firewalls. So instead of going to the public internet, just use your private connection. The direct connection you have connecting you to the cloud, or use that VPN connecting you to the cloud. Now you're secured. You're either on private wires or you're separated by an 802.1q tag or you're separated by encryption. You're not bypassing your firewalls. You're not bypassing your IDS systems. You have a full security posture. So what the Bastion host is just basically opening up and removing all your security. So that's why you use your direct connection. So Ronald Nadzo, if you have a direct connection, or if you have a VPN connecting you to your data center or the cloud, that's what you'd be using to access your data. But you don't need to secure your data in transit if it's going on a private line. Go hack this fiber optic connection that's buried under the ground. It's under the ocean. Hack this connection. Go dive 1,000 meters, go dig up a cable in the middle of the ocean where you don't know where it is. It's secure. It's a wire. You can't do anything. What would you literally have to do to access this wire? Well, you'd either have to dig under the city, pull out the cables. These are fiber optic connections. So you'd have to break the glass without anybody noticing while you're digging under the ground and tearing up the ground. Then you'd have to put a tap. Then you'd have to run another fiber optic connection to you being a couple miles away to see it. So realistically speaking, private lines are the most secure things in the world without encryption. Of course, you can run IPsec on top of it, and in certain secure environments we do, but we don't have any of these worries. It's wire. It's like the light switch in your house being plugged directly in the outlet. Pretty hard to hack that. Now, if it's a smartphone and it's connected to the internet, it's easy to hack, but we're trying to lock our stuff down. Go shut off a light. Go hack a light that's not connected to the internet, and a house that's not connected to the internet that's got no egress connections to anything. You won't be able to. So that's why we're using the secure connections we have to not have to deal with potential weak security holes. We're already using the strongest security in the world. It's wire. So hope I answered your question there, Ronald. Chris, if you want to go to the next one.
I'm not sure if we've got the time for this one, but I thought I'd put it up here. It disappeared. Here it is. Okay.
Ashwani Singh, I'd love to cover that, but that's the kind of stuff we cover in our Cloud Architect Career Development Program. It would take me at least 500 hours to go through some of those things with you. There's just too much to know. And I mean this in the most respectful sort of way. What people don't understand is if you're going to pay an enterprise architect or a really good cloud architect $300,000, $400,000, $500,000 a year, it's expected you have a lot of knowledge. And the knowledge they're looking for is that extreme business acumen, the leadership, the emotional intelligence, the sales skills, the ROI modeling skills, the ability to take vague problems and transform businesses. It's that. Now, most of these services that we're going to talk about, 2/3 of them you should never use in real life because they lock you into a single cloud provider. And there's much better ways to do a lot of these things. But in a solution architect course, if I want you to pass the exam, I've got to teach you what the vendor is saying. Now, if you're really looking for how to learn how to design an architecture, that's what we do in our career development program. We take 500 hours to teach people how to be employed and all these idiosyncrasies and all the tuning things. But it takes me 500 hours with them and about 8 months for people that have never been in tech and about 4 months for people that have been in tech, at least 250 hours for them. So it's not something I can do right now. I would love to. I really would love to. But it would take, 8 hours a day for a couple of months straight to actually do that, to really give you the architecture knowledge. And that's why we created the Cloud Architect Career Development Program for people that really, really, really want that deep knowledge, because it's just so extensive what we actually have to provide. Angelo, how do you add flexibility to your network architecture to allow for expansion? For example, the business may not want to allow interdepartmental communication now, but may in the future. You build your network right. And what I mean by that, you build your core, your access, your distributions, you set up your routing protocols right, you set up your what's the word I'm looking for, your IP addressing scheme right, and then you just inject whatever routes you want whenever you need it, and it's done. But of course, you're going to have your access control list, you're going to have your route filters along the way, you're going to have your firewalls along the way. So what you do is basically you build yourself the building blocks when you create it, make sure they can't talk to each other, and then just let them talk to each other in the future. Do it all the time, all the time. Build the infrastructure right, and it will scale to anything. Can we use VPC Pairing instead of a Bastion host? No, they're totally different. What is a private endpoint and how is it different from VPC Peering? An endpoint is just simply an entry point into something. VPC Pairing is two external entities that are connecting to each other. What diagramming software we're using? Well, here's how an architect like me designs things, John Clark. I've been an architect for 20-some years. At some point after a few years as an architect, as you move up the enterprise architect ranks, here's what you're going to be doing. You're going to be drawing little sketches on a piece of paper, and you're going to hand them to graphics professionals and they're going to draw it out for you. So in my youth, I used Visio. Now, most people use Draw.io or they use Lucidchart. Most of my drawings are done, the ones that look like this, the ones that I'm showing you are actually done here. Now, when we do our CCNA, we're going to make much prettier things, and we're going to use Adobe InDesign. The papers that I wrote at Cisco, I drew the diagrams, and then they were redrawn by a professional graphic artist in Adobe InDesign. So when you're really dealing with publications and really classy good stuff, it's probably Adobe InDesign for these big billion-dollar architectures. We cover gateway endpoints and gateway load balancers here. Not a lot, and here's the reason why. AWS is really cryptic with their gateway load balancers. And AWS is saying, hey, everybody, we got this new cool gateway load balancer, which you can use for your network devices. Okay, well, that's an AWS proprietary solution. Now, when am I going to use a network load balancer? I'm going to use it with everything. Every time I've got two firewalls, I'm going to use a network load balancer. Why am I not going to use a gateway load balancer? Because AWS doesn't publish any data on it. The speed, the throughput, nothing other than here, use this for your network devices. So right now, we're using network load balancers. You know why we're using network load balancers? Because we can use the same firewalls and the same network load balancers on Azure, AWS, Oracle, Dell, Palo Alto, and by using it and not using a gateway load balancer and keeping it to a network load balancer, I can create a beautiful multi-cloud architecture that's going to work everywhere. And I don't ever design a single cloud architecture because it's a single point of failure. So I'm not going to go into the, we did cover gateway endpoints, absolutely, but we're not going to go into gateway load balancers here. It's also not on the certified solution architects. What causes this fascination with the Bastion host? I mean, why do people do it? No one does this ever. Where did it come from? It came from the AWS certification courses being taught by people that have never been cloud architects or done any architecture work or done anything serious in their life other than work on a server. And they don't know security. So that's why this stuff is so dangerous, because you don't have any security architecture here. So for example, and I want to show you why, we will tell you that the Bastion host is by far the most dangerous thing that I've ever seen. So let's look at a traditional environment, what I consider to be a real security architecture. When customers approach me and say, Mike, I need security, I typically use like a content delivery network, and then I need firewalls. Now, I am never going to use WAF. It's not good enough. Plus, not only am I not going to use AWS WAF, I'm going to be on Azure and Google. So what am I going to do? I need a firewall that's going to work identically in my data center, firewall, and Google. So what am I going to use? I'm going to use a network load balancer to load share between virtual firewalls because they're going to sit on virtual machines, EC2 instances, what have you. And by doing this, now I've got a much better firewall than any cloud native service. Then what am I going to do? I'm going to use an access list to control my subnets, security groups on my servers. I'm going to put host-based firewalls, anti-malware protection, disable unnecessary services, patch all this. I'm going to be using Active Directory, some event-driven security. I'm going to encrypt my storage. I'm going to be having some audit logs. And heck, I'm going to add some machine learning into it. I'm going to send my logs into, say, Apache Kafka or Kinesis. And this was for AWS, but normally it would be Apache Kafka, which we would then send to a machine learning tool, and then we would visualize it with Tabula. So that's my security architecture. Notice it blocks everything. So in order to get into my systems, you got to beat all of this stuff. Now, here's the Bastion host. Let me draw one for you. You're going to see why I don't do it. And why I would say never, ever, ever, other than on a certification exam, even think about this. So in my previous environment, you got to breach my firewalls, my IDS, IPS systems, network access lists, my security groups, my host-based firewalls, my anti-malware protection. I've disabled unnecessary services and I got security. Now, here is the Bastion host concept. In the middle of nowhere, in the middle of the public internet, with no firewalls whatsoever, I'm just going to put an open computer out there. Hey, everybody, come hack me. Here's my computer. Hold on. Some of the shapes here are a little funny. So here we go. Here I've got a Bastion host. In the middle of the public internet, Bastion host. Now, this thing has two network cards. Network card A, which is connected to the public internet. Now we've got network, I'm not sure what happened there. We've got network card B, private internal network. Okay, so here you are, you're on the public internet, you have SSH access to this box. Okay, now this is just a regular computer. It's not a device like a VPN concentrator that was made by Cisco that had all the security vulnerabilities locked down. It's not going to be placed in a demilitarized zone. We've lost our firewalls, our IDS, IPS systems, our access controllers. We've lost all of it. Now you're just got that open box on the internet. Here, connect to it, and now you're in the network. So what you're saying is by doing this, what we lost effectively is this, 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 and this. And instead, it's come hack me. And I don't like, opening the door that says come hack me. So, that's why I don't use Bastion hosts. Now, there are Bastion host services that you could use, which are legitimate security devices that are locked down systems that only allow IPsec traffic in, and they're called VPN concentrators. And what you do is you set up your firewalls, and you create a DMZ that only allows IPsec traffic in, and then you filter, and that's how you deal with remote access and plays, not jump hosts. Jump hosts are like, hey, by the way, come hack me. This is like, how do you research me? So I hope I answered that question. And I know we took a little bit more time on that question. So I'm happy to answer some more questions because I feel like that was important instruction. Does everybody understand the Bastion host concept and why we don't recommend it? Mohammed Idris. In routing to provide full mesh connectivity for routers in IBGP, we use route reflectors. So is it the same in the VPC? Effectively the same. Now, Mohammed, we can't just call it a route reflector and a route reflector client like we normally would. We do VPC Peering to Cloudhub, which basically functions just like a route reflector. And then it becomes eBGP versus IBGP. So it's not exactly a route reflector, but it's based on exactly what we're doing with route reflector technology. And that's a great, great question. Also, is the concept of attribute to avoid loops like cluster ID if you use two route reflectors. On the data center connecting to the cloud, yes. And the cloud stuff, we're so limited in what it can do. We're using a route reflector like services. And no, obviously, clearly, Mohammed, you're a networking professional like me. I'm so happy to have you here. Tom, so no Bastion host means don't use virtual machines in the public subnet for with SSH. Exactly. So, if you were taking the Google Professional Cloud Architect exam, they would tell you, please disable SSH on anything that's internet facing because they don't even want it open. Now, Google has a little bit more architecture in their exams. Google's more function on, architectures and case studies, while AWS exams are more about the name of the service and how they configure it. But even still, the Google exams aren't that architecture. There's still some engineering in them. Chris, are there any more questions?
Oh, that's it for right now.
Okay, wow, we're tracking, we're flying. Everybody having fun? If you're having fun, type hashtag Cloud Architect and then hashtag Cloud Hired. Love to see a bunch of them. Hit the like button, the comment button, the subscribe button. And when I see a bunch of them, I'm going to get ready. I'll be all kinds of excited to get back to the next group of things. Marla. Marla is one of my extraordinarily great cloud architects. Cloud Hired, Marla. Jeannie, I'm so happy to see you. Cloud Architect. Raphael, wonderful. Pierre, fantastic. Leo, fantastic. Debbie, I'm so happy to see you here. Mr. Singh, Cloud Architect. Tom, high availability. Okay, fantastic. Kenny, Hand of God. I forget, Hand of God, are you in Greece? Neil, fantastic. Mel over in New York. Noel, Rajat. Oh, this is great. Love having all these folks over here from all parts of the world. We're all having fun. So, wow, this is fantastic, fantastic, fantastic. So we're going to get into some network control lists. But you know what? I'm actually curious. Loving all these cloud hireds and cloud architects. So you just joined our class. Congratulations. Welcome. I can't wait to work with you. Jamal, fantastic. Eva Doikio, fantastic. Emmanuel. Saeed, welcome. Jamal, welcome. Mr. Gee, I love that. Are you a jujitsu person or you like to cook with Gee? Oh, Luke, nice to see you. Mr. Binary, as I like to call you, VNHG, Randy. Okay, I'm loving this. Georgetta Ipadeka, thank you so much. Roger Marine. Oh, wow, I'm loving this. I love seeing people from all over the world. Okay, so let's talk about some network ACO. And yes, I enjoy this because I love tech. And you know what? When people know you love tech and it's your passion and it's your hobby, you're never going to mind doing it. So when everybody says, Mike, which career do I want? I say, what makes you happy? Because I want you to be the best in the world at whatever you do. So you don't work. I don't like working. Who likes working? I like doing my hobbies and getting paid for them. So there's there. Alonzo, let's welcome Alonzo. Alonzo is a critical member of my team. He's leading our cloud engineering program. So welcome, Alonzo. We're super happy to see you here. Okay, everybody, let's talk about some network access control lists. Network access control lists are just like access control lists on any other router. They keep traffic out of a subnet. So that's what we're dealing with. We use access control lists to keep traffic out of a router. Well, with AWS, we have a next network access control list. And what do you think that is? It protects the subnet. So basically, we've got virtual routers, we've got a virtual access list. So an access list is a stateless device that is a simple packet filter that says deny or permit. And that's it. Now, access control lists are processed in order. And this is the ugliest thing you'll ever want to see in your life, the way the access control lists are processed in order. Order matters. And if you get the order wrong, and every one of us at one point has gotten the order wrong of an access control list. And when you get the order wrong in your access control list, you know what happens? You break stuff. So we'll talk about it. The default policy of any access list, any security group, or any firewall is deny. So you want to come into my house with the door locked? Deny. You want to get past my firewall? Deny. You want to get past my access list? Deny. Now, Alonzo's my good friend, a really close friend of mine. Now, I want Alonzo to get access to my house whenever he wants it. So I give Alonzo a key. Now, on an access list, I say, permit Alonzo entry into Mike's home. If I do that, he's allowed in. But the standard access list is the locked door. Nobody gets in. Alonzo's my good friend. Alonzo, here's the key. He gets in. So with an access list, it might say permit Alonzo, permit Ivodoikia, deny everybody else. So that's what we're dealing with. Now, I want you to think about this. Order matters. So if my first thing says permit Alonzo, my next thing says permit Ivodoikia, and the third thing says deny everybody else, that's going to work. Now, what if I said deny everything, permit Alonzo, permit Ivodoikia? What happened? Thing comes in, hits the packet filter. Deny everything. Here's what happens to all the people. They're thrown out. They can't get there. So when you make your network access list, permit the things you need. There's a default deny at the end of them. So permit what you need, but permit it in order. Meaning, if you have to deny one host, permit the subnet and then deny the next line, the next host. So make it in order. Order matters. So when you're making an access control list, guess what? On a Cisco router, a Juniper router, a Palo Alto firewall, a Cisco firewall, a Checkpoint firewall, or AWS, here's what you do. You specify the source and destination, 192.168.1.1 going to 1.2.3.4, the protocol, TCP, UDP, ICMP, and the port number. Port 80 for web, port 40 for HTTPS, port 22 for SSH. And that's how it works. It's the same thing. So a network access list is the same thing, whether it's on Cisco, Azure, Oracle, it's the same thing. It's a basic packet filter. They call it an Azure ACL. Same concept. It's the same thing. So it just protects a subnet. So what's it looking like? Here's what I said. I gave you the example of how to do it wrong. Let me show you wrong again one more time. Improper technique. Rule 1, deny everything. Rule 2, permit web traffic. Now, I have to make them inbound and outbound because there's no state with an access list. Remember when I told you yesterday that the stateful means this. Here's my phone. Pretend my phone is a firewall. If I go from my device through my firewall, out to the internet and comes back, the phone or the firewall remembers that I initiated the traffic and lets it come home. So that's kind of like Alonzo's staying at my house, and I hope Alonzo stays at my house someday very soon, because there's some things I want to do with him, some sporting events that I want to take him to. So Alonzo stays at my house. Alonzo leaves the front door, and he's allowed to return back because he's my guest. Why? Why? So let's say you've got a construction worker in your house. Your front door is normally locked, but you invited the construction worker in. The construction worker walks to their truck to get a tool, and they come back in. They're allowed back in. Why? Because you know it's them. So what a firewall is stateful, it watches your traffic, but access controllers are not stateful. So it has no means to know that you allowed the traffic in to allow your return traffic, because it's not tracking the state of the connection. And that's what we're talking about. So a network ACL is, realistically speaking, and I want to show you the right way to do it. Inbound, just permit the TCP port 80. Outbound, permit it back out, and there's nothing else to do. So kind of keep that in the back of your mind. Network ACLs, whether it be an Azure ACL, an access control list on a router, it's all the same thing. It doesn't matter. So I want you to see from a security perspective. So you've got your router pointing to the internet. We've got our network ACLs protecting a subnet. We've got our security groups protecting a host. So let's talk about the security groups next. Security groups are effectively a stateful inbound firewall to the server. So instead of a network ACL just being a packet filter, a security group is an actual firewall. Stateful meaning it tracks the connection. So let's say what a security group is. It protects your servers, or it protects your servers, or maybe your load balancers. What do? You put an actual firewall on. It's called a security group. That says, Azure will call it a network security group. It says, allow port 443 into the web server. Now, it's a stateful firewall. So Ivdokia is connecting to port 433 to the web server. She goes through. Now the web server answers. The firewall says, that's Ivdokia. She's permitted. Her traffic's coming back because it's stateful. So when you're dealing with stateful devices, they track the connection. They'll say, that's Alonzo in, Alonzo out. That's Ivdokia in, Ivdokia out. This is Smokey the Bear. Smokey the Bear is not permitted. Block him. Oh, Abigail came over, permitted through, and block her. So that's what we're talking about, security groups. We're allowing ourselves to put a firewall in front of the device. And that's how we create security. So kind of keep that in the back of your mind. So a security group is a stateful firewall that protects your devices. Excellent, excellent, excellent stuff. Very useful as part of it. So if people say, am I going to use a network ACL or a security group? I'm going to say you're going to use both, because they do different things. Security is like an onion. You want so many layers that you peel a layer, you peel a layer, you peel a layer. And then you've got the total package. So kind of keep that in the back of your mind. So that's what you need to know about security groups. They protect an instance or a service. Security groups support allow rules. Allow Ivdokia, allow Alonzo, allow Chris, allow Abigail, allow Chow. That's what they're from. Allow Jazz, for example. That's what they're doing. And again, going back to this, I had somebody draw for me a security group to make it look this way. And what are we talking about? We've got the routers. We typically are going to have some firewalls and IDS, IPS systems. Then we're going to have our network ACL protecting the subnets. And then we're going to have the security groups protecting our instances. Now, of course, on our instances, we should disable unnecessary services, patch them, put a secondary host-based firewall, add some anti-malware as part of the security thing. But, that's talking about enterprise-grade security, which is way, way, way beyond the scope of the AWS Advanced Security. That wouldn't even touch it. What I'm talking about now is big security architectures for the cloud security architecture, the cloud architects that are getting involved in real enterprise organizations. So pretty interesting stuff. We teach that in our cloud architect career development program. But make sure that you guys understand security. Let's talk about some means to improve the network performance in your VPC and what that would look like. So when you're dealing with networking, traditionally we're thinking of routers and switches and all these cool devices, but you got to remember in the cloud, it's just a virtual network in a data center. So we're going to talk about some networking optimizations in this section. We're going to talk about placement groups. We're going to talk about PCI pass-through, otherwise known as single root IO virtualization. I can't even imagine who would come up with that creative name. Then we're going to talk about a fancy driver, which has to be called the Elastic Fabric Adapter because it's AWS and they have to have Elastic. We'll talk about Route 53, which is the DNS, and then we'll talk about load balancers. So this is the really funny stuff. Fun stuff. So let's first talk about placement groups. And, this is something you should think about. Now, there are times where latency matters so much that if you can do anything to shave the latency down, you do so. Now, realistically speaking, if this is the situation, you've got to shave your latency down to 0, you're probably better off being in the data center and skipping the cloud completely. But if you're trying to create, Hadoop clusters and some of these other things in the cloud, sometimes you want to put your stuff close to each other. So let's think about this. If you put all your eggs in one basket and they're all close to each other, guess what? Your performance is going to be great. If I put 1,000 people in the same room and they can all touch each other real fast, right? They're probably also sweating, feeling sick, short of breath, yelling and screaming at each other. But if I put 1,000 people in a 100 square foot room, they can all touch each other fast. Well, here's the thing. We can do the same thing in networking. And so AWS has the concept of placement groups. All clouds, your OpenStack cloud has it, your Google cloud has it, your Azure cloud has it, and that's basically how fast you want to group your things together. So we're going to talk about 3 ways you can group your systems together for high performance computing to try and make the cloud perform relatively well. So let's talk about them. The first is something called a clustered placement group. And a placement group, realistically, is just where you place your stuff. So where you place your stuff, the proximity to each other can affect its performance. So I'm going to give you the 3 kinds of placement groups we can use. Now, the first kind of a placement group is something called a clustered placement group. Now, I want you to think about this. And I'm going to ask you all to type the problem in about 30 seconds. So because I want to know that you're all thinking like architects. So cluster placement group. We place all of our virtual machines in the same physical rack that uses the same physical power supply, that uses the same physical switch. And in most cases, we've got all of our servers, all our virtual machines, all sitting in the same server, on the same rack with the same power. Now, by doing this, by having everything with a few feet for each other, we can shave off milliseconds of latency because the speed of light going 3 inches is not that far. So by doing this, now, can anybody tell me what the problem would be of having all your stuff in 1 or 2 servers, all plugged into the same power supply, all plugged into the same switch? If you think the clustered placement group is a safe idea or a good idea, you tell me what the main problem is with this. Okay, I'm seeing my students pop in so far. Exactly, Jeannie, it's a single point of failure. What if the power fails? What if the switch fails? What if the server has a failure? We're done. Done. So if we have one cluster placement group and we want high availability, what must we add? A second cluster placement group. 1 is none, 2 is 1, and 3 is greater than 2. So if we're going to do something this risky, and there's times where we need to do this because we need that performance, we must choose 2. Do you know I've worked for banks and we've had 2 little racks that literally have these like $10,000, $100,000 servers and a $500,000 high performance switch, and they're coming in with multiple power supplies on multiple circuits all in the same rack and multiple switches, but we're doing it and we're creating multiple side by side. And these things in the right bank can make a difference of billions of dollars a year in earnings because they're so fast. And if you're going to process a trade of 1 million shares and it's gone up $5 because of Newton, you can catch it at the cheapest price along the way up before everybody else buys it. It's a competitive advantage. So clustered placement group, 1 is none, 2 is 1, 3 is greater than 2. Realize the clustered placement group, all your eggs in a single basket, is the most risky thing you could do, but it also gives you the greatest performance. So what's it look like? It looks like that. Many single points of failure, single switch, single rack, single power, single cable. It's a disaster waiting to happen. But If you need the performance, you have no choice. So keep that in mind. There's a time and a place for everything in architecture. There's always reasons why for doing this. So next, what do we think we can get a look? What do you think would be the next best way to move up? Well, we could go from the clustered placement group to something a little different, a little better, called the partition placement group. Now, this is going to improve it a little bit. It's also going to slow it down. So again, 2. 1 is none, 2 is 1, 3 is greater than 2. So let's go back to this. What is a partition placement group? You take your systems and you spread them across multiple racks, which means multiple switches, multiple power supplies, multiple cables. But you typically, not always, you typically still place them relatively close to each other. So you've got good performance, relatively good performance, and it's a lot safer. So what does it look like? It looks like this. Use 3 racks in a single availability zone. And by doing it, they're in the same building. The latency is extremely minimal. We've got great performance. So the partition placement group is a little bit slower than the clustered placement group, but it is much safer. So what do we recommend? 2 of them, even though we've got a little redundancy. So stick 1 in 2 different availability zones in case it goes down. Or stick 2 in the same availability zone and another one in another availability zone. When we're dealing with this kind of performance requirements, cost generally is not an object. It's all about meeting the performance requirements. There's 2 kinds of architects out there and architectures you do. Architects like me go to the leadership, we find about the business, and we solve business problems. Then we tell the customer what it's going to cost, and we do an RM model, and they say, yes, Mike, I love your $200 million solution. It's going to generate $1 billion in business value. No problem. But some of these architectures we do are like, Mike, help me with my yoga studio. And we got to shave out as much money as we can. So there's all kinds of architectures and all kinds of use cases. The key for you is knowing the right one. So let's talk about spread placement groups. Spread placement groups are realistically the next alternative. What a spread placement group does is enable you to spread your load across multiple racks and different availability zones. So let's think about this. Now you're in 3 data centers. Well, we've got greater availability, theoretically, because we can lose a data center as long as there's not as long as there's not a network failure, a security failure, or a control plane failure, that second availability zone can take over. So you can think about that. So spread placement group, spread across racks and data centers. So let's think of let's think about this and what it looks like. Spread placement group, availability zone 1, availability zone 2, spread across racks. Now thinking about this, what do we really think in terms of performance of this? Do we think this is going to be anywhere close to the clustered placement group? No. But is this much more redundant? Is this much more higher availability? Yes, it is. Dramatically better. So why are we using spread placement groups? Because it gives us the ability to still cluster our stuff in a relatively small space while having much higher availability. So now you know the types of cluster placement groups. Clustering in them is just a means to get your stuff closer to each other. If you get it close to each other, here's what we do. By getting close to each other, reduce latency. So let's talk more about networking performance. We'll talk about enhanced networking. Well, if any of you have ever created a Hackintosh, or any of you have worked with VMware, and you've dealt with the need for extreme performance, you know what I'm talking about. But if you don't, I'll explain it. When you deal with virtualization, are you guys all familiar with server virtualization and containers and things like that? So when you deal with virtualization, you basically have a server, you install a hypervisor, the hypervisor manages the memory, the disk, and when you create your virtual machines, for which it manages the memory, CPU, etc., you select your number of cores, you select your DRAM, you select your hard drive space, and you select your network adapter. Now, these are all virtual appliances, virtual devices, virtual video cards. virtual network cards. So I'm going to ask you this question. Which do you think performs better? Software or physical hardware? Software, which hits the CPU for a general purpose CPU that can do anything, or physical hardware that's got an application-specific integrated circuit that could be 10,000 times faster than software? Give you a concept. I've got some blockchain people on here. I can take a machine for about 2,000 watts, and I can do, literally speaking, about 100 terahashes a second across of some ASIC chips. Now I could buy a server. I could buy $100,000 of GPUs in that server, and I might be able to go with 10,000 hashes on GPUs. Now I could buy a $100,000 AMD EPYC server, and that server itself might be able to do 1,000 hashes versus the 100 terahashes on hardware, because hardware is faster than software. Hardware is always faster than software. So what is single root IO virtualization? It's where you're taking a physical network card and you're pushing it directly into the virtual machine. So the virtual machine has access to this. Now, if you're ever doing any machine learning environments on the cloud, guess what? You're going to have a virtual machine that's got an NVIDIA GPU in it. And what is that? The GPU is passed into the virtual machine. We're bypassing all of it. So we're getting straight into the hardware. So that's called single root IO virtualization. I like the name PCI pass-through because we're taking a PCIe card and we're pushing it into our virtual machine. So kind of keep that in the back of your mind. So that's one option that we have for good networking performance in the AWS cloud is as follows. We can use single root IO virtualization, SR/IOV, or we can use a special driver. So AWS came up with a new driver to give better performance to a virtual network card, which they call the Virtual Fabric Adapter. I think they call it Elastic Fabric Adapter, actually. And what is it? It's just another piece of software. And theoretically, this device driver can go up to 400 gigabits per second at some point in the future. It's nowhere close to that right now, but it's a new driver. But here's the thing, hardware, software, we're not even in the same universe. So single root IO is really great, especially if you can be pushing 100 gig network cards into your system. But the Elastic Fabric Adapter is still quite good. So keep that in the back of your mind. We're going to get into DNS, and DNS is a relatively heavy topic. So I'm going to ask you all if you all have any questions before we get into DNS, because DNS is going to get ugly. We've got a lot of stuff to cover in there. So are there any quick questions?
Give me just 1 second.
Sure. I want to make sure everybody has a wonderful experience. While we're at it, please make sure you download our free ebook. Please sign up for the free CCNA program that's coming. And also while we're at it, please make sure you sign up for our architecture class where we're going to teach you how to design an architecture.
There were questions. I just have to find them.
That sounds good. I see some are popping in, but I can't really look at them and see them and still try and figure out. Jamal, ACL is applied on the subnet level. Security group is applied on the server level to the service itself. So when you migrate a workload from on-premise to AWS, how is the network part taken care of? The network part is designed by your network architects and your cloud architects, and your cloud engineers are the ones that are going to configure the things that you tell them to do. So that's how that's taken care of. Can you secure your instances using a security group only? Not even close. A security group isn't even 10% of the protection you need for security. You got to remember a couple things on the cloud. The cloud is just a little bit less secure than the data center. See, in the data center, we can know our ingress and egress points, and we can secure all of them. In the data center, we can stick our physical firewalls, our physical IDS, and we've got access to maximum security. On the cloud, we're using a shared system. We don't have access to the world's best firewalls anymore, the best IPS systems. The closest thing we can do is use virtual firewalls, which we're going to have to do. The virtual firewalls, we're going to take, and then we're going to use network access control as security groups. We're going to need host-based firewalls, malware protection. We're going to need IAM. We're going to use encryption. the security group doesn't even scratch the surface of necessary security. So not even close. But I do like the concept. It's security is like an onion. You peel the one label, the next layer, the next layer, the next layer. If you don't have about 10 or 15 layers of security, here's what's going to happen. You're going to get hacked. Chris, if you want to bring in the next one. Tech with Mufaz, what is the point of a partition placement group? If you need high performance and you don't want a single point of failure, that's what you're using. Partition placement groups aren't something that shouldn't be recommended. There's times in a place where it's actually useful. The cluster placement groups are really risky, and there's still some customers you have to do it for. It's a matter of the right thing for the right customer at the right time. But great question. The point of it is high performance computing because your stuff's closer to each other. Chris, if you want to bring in the next one. In the case of which placement group, to be fair, I actually don't know if there's a difference in cost between one or the other. I don't think there is. What is a control plane failure? That is a great question. And so whenever we're dealing with a cloud or even a network, we have two parts of the cloud. We have the part that orchestrates it, and we have the servers. So if any of you guys were going to build a cloud, here's what we'd do. We would build a data center. We'd get our Cisco routers and switches, our Juniper stuff, our F5 load balancers. We'd be buying our storage from Dell EMC, all this stuff that we network architects and data center architects have done for 30 years. Then what we would do is we would take a bunch of servers, and on these servers, we would install a control plane. And a control plane is like the puppeteer. It's in charge of everything. You create a virtual machine, and John Clark, it says, send it to server 2700. I create a virtual machine, and it says, send Mike's server, where this capacity is server 3,569. Nobody knows. This thing goes over here. They typically have a Mongo database that's no SQL database that's keeping track of customers' data. You add your thing, there's there. All this stuff is managed. It's all managed because everything's virtualized. So you got the brain of it's the control plane. So what happens is anytime you're dealing with a control plane failure is if anything hits the orchestration of the cloud, then we just have a bunch of servers and storage, and they're no longer cloud. So when you can't access the management console, for example, like there was an outage that affected the management console, which we heard was an impaired network device, and the impaired network device in one US region made it that users in South America couldn't access the management console, or Europe, the Middle East, or Asia. Most likely, there was something that went wrong with that orchestration plane, because having a network failure in one building does not take out an entire cloud and multiple availability zones and data centers for 8 hours. So keep that in your mind. So that's a control plane failure. If you have networking and you've got a software-defined networking, there's servers that are orchestrating how your data is forwarding through them. Again, those servers go down and you lose it. And that's why organizations would never use just one internet service provider. They use two, because it's not just the links that can go down, it's the routing. The routing is the control plane for the network. With the cloud, we've got the cloud control plane. So when my students build a cloud in my cloud architect career development program, to be fair, I don't have any student that goes through my program and doesn't build a cloud. Because when we're talking about certification, we're talking about the name of the service and how it works. You really need to know every element of the cloud. So every one of my students builds an actual cloud. So they set up the control plane, the data plane, et cetera, and then you know all the things. So the next time you hear an outage report and you start looking at these things, you'll be able to know what's real and what's not real, because you're going to understand how the cloud works. So I kind of make that. So the orchestration. So in Kubernetes, you've got the orchestration piece. That's the control plane for Kubernetes. I hope that makes sense. And routing, we've got a routing protocol that builds the map. That's the control plane. Tom, we're going to be talking about Route 53 in 1 minute. So we'll leave that to that section because it's a great question. Are there others, Chris?
Those are all the content-related questions.
Okay, well, then let's do this. Let's end the day with a nice discussion of Route 53 and the way to get your DNS. Networking stuff. The networking stuff's the most fun. So then again, I'm a networking person. Sounds good, Chris. So let's talk about DNS. And we're going to use the term Route 53. And just realize Route 53 is, again, the AWS marketing people's turn for the domain name system. So in the domain name system, you've got servers, and there's a routing. And guess what? It's the same thing on every cloud provider, every internet service provider. So if it's Azure, Google, Oracle, Dell, Palo Alto's cloud, Cisco's cloud, IBM's cloud, or heck, your own cloud, you're going to be using DNS. And for the most part, the names will change, but the systems will be identical. So what is DNS? DNS maps a name to an IP address. So if Eva Doikje goes to her system and she does an ifconfig on her router, and she gives me her public IP address, I can connect to her directly through her public IP address. And it's going to be something like, well, whatever, if I knew her IP address. But if she made evadoikje.com, I could remember evadoikje.com. Now, even after I know her for months, I still struggle to spell her name. But, even though it's a Greek name, which is even sillier. But, the point is I can remember evadoikje.com. You can remember www.gocloudcareers.com. You can remember www.cindythecat.com. It's easy. So DNS maps a user-friendly, fun name like Elastic to an actual IP address. So keep that in the back of your mind. So that's what we're talking about with DNS. And this whole section is DNS. AWS calls it Route 53. DNS uses TCP and UDP port 53. So the reality is this is quite a good name. This is not a cryptic marketing name. This is feasible. Now, I still wish they'd call it DNS because I like to call things what they are, but all right, whatever. So DNS is all about mapping a name to an IP address. So I go to my browser and I type www.amazon.com because I want to buy Cindy cat food. So my computer does something called an NS lookup. The NS lookup resolves the IP address for that name. And then I access that IP address. My computer goes to the routers via routing. So that's what DNS is. It maps a name to an IP address. So here we are. We're on my computer. On your computer, if you're on a Mac, if you're on a Linux system, you can probably do this in Windows too. You go to the command prompt or the terminal prompt, type nslookup and pop an IP address. And here's what I did. nslookup, www.amazon.com. What do I see? I see these two DNS servers, which is something called Anycast, which we can talk about if you guys like. Definitely, we covered that in the Certified Solution Architect Professional, but we can talk about it here if you guys want. Here's what I find. I find Amazon. I get a CNAME record, which is over here. And then I actually get the actual address of the server. And this is this ugly, ugly CloudFront distribution name. But there'll be a CNAME record that's going to map Amazon.com to that. So you're not going to know about it. So that's what it is. On your computer, if you ping www.cisco.com, go ahead and do it. Take a command prompt, ping www.cisco.com. I promise you're going to find the Cisco's IP address name. Or better yet, type nslookup, www.cisco.com. You'll get its IP address, and now you'll know. So let's go back to this DNS kind of thing. Let's talk about domain names. Domain names, and I'm going to keep this slide here for one more minute. Domain names can be broken down into three separate sections. A fully qualified domain name is going to be as follows. It's going to have a host name, a domain name, and a top-level domain. The top-level domain is going to be like a .net, a .uk, a .edu, a .com. The domain name is gocloudarchitects.com, and the host name is www. Now, if you're on AWS, your host name might be cindythecat.gocloudarchitects.com, and that would be an appropriate host name for her, for Cindy the Cat's computer. And yes, Cindy the Cat does have her own computer. But she's a little bit of a pampered little friend, but so be it. So Cindy the Cat has her own computer, which she pushes her keys on. She eats the keys, but it's an old computer. And this way she can sit in my office while I'm working and do that if she's not sitting on my lap. And she's not on my lap right now, which is really sad and unfortunate because he's where she usually is. So keep that in the back of your mind. So let's talk about DNS records. And you must know some of these. A DNS record or a zone file, realistically speaking, provides a specific set of instructions. And these instructions are going to be placed in DNS syntax, which is the format of the text file that you place this information. Your DNS record is going to include something called a time to live. What is a time to live? A time to live is as follows. A time to live is how long your information is going to stay current. So if you have a time to live of a month and you change your website's address, DNS is going to cache the old information for a month potentially. So the TTL is how long stale information goes. Now, remember, the longer the TTL, the less overhead, the more stable your systems are. The shorter your TTL, guess what? The more overhead on your systems, but the more rapidly they change, the more close they are to being accurate. So in either case, you're in good shape. TTL is typically measured in seconds, but can be done otherwise. Now there are a tremendous number of types of DNS records. We'll talk about the key ones that you need to know. But before we do, I'm going to do it. I'm going to talk about Anycast because it's important. It's kind of ugly, and I want you to understand it. So I previously told you the truth, which is that every device in the entire internet, if you want to be able to communicate it, needs to have a different unique IP address. I see Ciao, Abigail, and Ivodoikia. So all three of them I see with the blue wrench. They're over there. They all have their own systems, and they all have their own unique IP addresses. Now, let's say right now, I decided that Abigail, Ciao, and Ivodoikia are all going to help me right now respond to all you guys. But instead of leaving them as Abigail and as Ciao and Ivodoikia, I named them all Mike. So there's 4 Mikes out here, and they're all responding as Mike. And whether it's Ivodoikia responding or Ciao responding, they're all responding as me. So what is Anycast? Anycast is when you have 2 DNS servers and they have the identical IP address. Wait, Mike, you just told me that every device on the internet needs to have a unique IP address. So how's this going to work? Well, in Palm Beach, Florida, I'm over here. In Hungary, Ivodoikia, no, are you in Hungary? Oh, well, apologies if I got that wrong. So let's assume Ivodoikia is in Hungary. She's still got the same IP address. So I'm 8.8.8, which is Google's IP address. Ivodoikia is 8.8.8, and Ciao's 8.8.8. So now Ciao, let me say Abigail, because I know where Abigail's out. So Abigail's in the Virginia metro, and she's 8.8.8. I'm in Palm Beach, Florida, effectively at 8.8.8. And Ivodoikia is 8.8.8 over there in Europe. So here's what happens. Chris is in Florida. Chris lives in Florida. Chris goes to his www.gocloudcareers.net. He hits his local DNS server, which is 8.8.8.8, which is me. And when the routers go to the routing table, he sees the closest 8.8.8 is in Palm Beach, Florida. So Chris comes to me because the internet routing sees it as 8.8. Now in the internet routing, there's an 8.8 floating somewhere else, /32, and there's another /32 8.8 floating somewhere else. But the 8.8 is closer to me. So now, poof, I'm down. My DNS server just died. I'm sleeping. Now, Abigail's in Virginia. Virginia is the next closest DNS server. She's somewhere around there. So now Chris in Tampa, Florida goes to www.gocloudcareers.net. He looks to the routers, look in the routing table, and wow, the closest 8.8.8 is now in Virginia. So his router sent him to 8.8.8. Now, Abigail is not feeling well. Abigail says, Mike, I'm tired of answering people's requests today. I want to have some chicken soup. I want to hug my cat, and I just want to rest. So we give Abigail the deserved rest. We wish her a super speedy recovery. Abigail's amazing. We want to make her happy. So, maybe we take good care of her, send her some chicken soup, some cat photos. She's now asleep. Now, Chris still wants to go to www.gocloudcareers. Now, I'm dead. Abigail's sleeping. And the internet redirects her to the closest 8.8.8, which is over in there in Hungary or Europe. Okay, so now that's how Anycast works. And how does this work? In your computers, they're configured to one address. Just one address. Please get some chicken soup, Abigail. So we're connected to a single address. and by my computer, which is statically defined. And if you want to know what my IP addresses on my computer are, or your computer, it's pretty easy. Go to a command prompt and type ipconfig/all. I'm not going to be sure how I can share that screen. So I don't want to make Chris have to teach me how to do screen sharing, etc., etc., etc. So kind of keep that in the back of your mind. So that's kind of how these things sort of work. I love networking, always will, and love teaching it. Then again, I used to teach engineers at Cisco and other companies, networking too. So I just love it. So when I worked at Cisco, I would teach the engineers architectural concepts all kinds of times. It was so much fun. So AWS Route 53, I had told you there are some records you should know. And we're going to talk about the few that you need to know, but you need to know the A record. IP address to cindythecat.com. That's an A record. Now, with IPv6, I have something called an AAA record, which is my IP address to gocloudcareers.com. Then, if I want to receive mail, I've got an MX record. I might have a start of authority record. I might have a sender policy framework, which identifies things. The point is, we're going to have records, and we need to know some of the records, not all of the records. The records I want you to know are as follows, because as a cloud architect, you'll be dealing with them. The simplest and most fundamental records you'll work with is something called an A record, or the AAA record. It's just A record for IPv4, AA record. Maps a name to an IP address. That's it. Now, let's talk about a same name record. A same name record basically maps one domain to another domain. So when I started Go Cloud Architects, I came out of retirement, and the reason I came out of retirement is I saw the AWS training that was out there, and I knew it was so bad I had to do something about it. So I started Go Cloud Architects, and the first thing that I wanted to do was to get all those AWS certified people. They couldn't get hired. Cloud hired, so I formed the company, and my students are getting hired every day. Now, after my students get hired every day as cloud architects and they're super successful, people started to come to me and say, "Hey, Mike, I want a cloud engineering program." And I said, "Okay, I'll put one of my best people on it, and I'll work with them on creating it." And then I spoke to some leaders at some of the companies, and they're like, "Mike, I want you to create an executive leadership program for us." And guess what? I created that. So I changed my name of Go Cloud Architects to Go Cloud Careers. But everybody knows us as Go Cloud Architects. So here's the thing. What are we going to do? We'll create a CNAME record that maps Go Cloud Architects to Go Cloud Careers. And then all the people that know us as Go Cloud Architects will still be able to find us. So CNAME records, you're going to be using them everywhere to map a domain to another domain. Either like in our situation, our company grew too fast and we have to change the name, or we're going to basically putting a situation where you're going to get an ugly CloudFront name and you want to make it look pretty like cindythecat.com. So A record maps a name to an address. CNAME record, it's like an alias record. It maps one thing to another thing. So keep that in the back of your mind. The next record that I'd like to talk about is something called an NS record, which is a name server record. And all that does is identifies the name servers that are responsible for your DNS zone. These are your authoritative servers that are going to propagate your namespace to the whole internet. And of course, these can be several entities. The next record you need to know is an MX record. So if any organization wants to set up a mail server, an Exchange server, for example, like this, guess what? What is that? We need an MX record. Otherwise, we won't be able to send and receive emails. So actually, I think it's more receive email. But so an MX record enables us to receive email. I don't know of any company that's not using email. So pretty much, you're going to be creating you need to know about MX records that your cloud engineers or sysadmins will be doing. They'll be building these, but you'll at least be doing them in your design. The last record that's pretty critical to talk about is the start of authority record. And what is a start of authority record? It tells you the name, the primary name server for the domain, the responsible party for the domain, a timestamp, when things were changed, etc., etc. So those are the key records. A records maps a name to address. CNAME record, it's kind of like an alias record. I saw somebody say Bitly. Yeah, exactly like Bitly, where you shorten your URL and it maps one thing to another. Exactly. We've got an NS record, which identifies your DNS servers, an MX record, which is necessary to receive mail. And of course, we've got the start of authority record, which is the name servers for your domain. And there you go. They're your basic DNS records that you need to know as a cloud architect. So let's talk about routing policies with DNS. So when you're dealing with AWS, it's relatively scalable. The Route 53 is a good solution. And it's a relatively low-cost method for routing your traffic. And Route 53 supports IPv4 and IPv6. Basically, Route 53, just the AWS implementation. Now, when we're dealing with DNS, and thank you so much, Tech with Mafaz, but when you're dealing with DNS, you have lots of routing options where you do it, but in order for it to work, you have to know if your devices are there. So, Chris, can you actually hear me through StreamYard? Okay,
Yeah,
so
yes,
maybe not.
I can.
Okay, so I want you to I'm going to give you a health check, and I want you to respond.
Hello?
Yeah,
Hello?
no, I'm going to give you a health check. Chris, are you there?
Yes.
Chris, are you there?
Yes.
Chris, are you there? Okay, I'm going to ask him again. Chris, are you there? Chris, are you there? Chris is not there. Do I want to send any more traffic to Chris that's not there? No. So here's what a health check is. I've got two sets of people. I've got Chris on one end and Alonzo on the other end. Alonzo can't hear me because he's on YouTube, and there's a delay. That's why I asked Chris. So Chris, are you there? Chris, are you there? Chris, are you there? Nope. Reroute to Alonzo. So that's what the concept of a health check is. In routing protocols, we have hellos. In BGP, we have keep alives. Are you there? Are you there? Are you there? With DNS, we have health checks. With load balancers, we have health checks. It is the same one, the same thing, exactly what we're talking about. So keep that in the back of your mind. So now let's talk about routing policies. What are they? We've got the following routing policies with AWS. We've got simple routing, which we'll talk about. We have rated routing, which we talk about. We have latency-based routing, which we'll talk about. Failover routing, which we'll talk about. Geolocation routing, which is quite simple and easy to talk about. Multi-value answer routing, which is all very goofy. And geo-proximity routing for traffic flow. I'll go over it, but I kind of like knowing where my stuff is going to go. So let's talk about simple routing. Basic. A DNS A record. Map a single name to an IP address. That's it. Go Cloud Careers to its IP address. Ding, ding, ding. Everything's great. Let's talk about the next one. Let's think about an environment where you're implementing a new website, for example. Here's what I mean. You've got your current website, gocloudcareers.com, www.gocloudcareers.com. Now, in the back end, I hired a new set of web developers, and they optimize my site. They make it big and beautiful. But I don't know if the site's going to work yet, right? It's a brand new site. So with weighted routing, I could send 90% of my traffic to the old website and 10% of my new traffic to the new website. And now the new website's up. Ivadoika says, Mike, I love it. Abigail says, I love it. Chal says she loves it. Tech from Mufaz says, I love it. Alonzo's like, yeah, Mike, this is good. I then shift all my traffic to the new website. But what happened if I released a new website and it crashed? It crashed. Now, by going to the website and it crashed, I don't want to use that website again. So DNS will send it to all the healthy website. Now, once I know my users love my new website, I'm going to shift all the traffic to the new website. So when you're dealing with blue-green deployments, for example, and you're dealing with automated releases, you can use DNS, specifically weighted DNS, to test it on a subset of your users before you shift all your traffic. This is agility. This is awesome. This is how you should be testing new websites. Sending a percentage to one thing and sending another one. What's the next option we have here? Latency-based routing. Latency-based routing looks at where you're at, your source address, and determines the latency. So what if I had a website in, let's just say Europe, I had another website in America, and I had another website in Brazil. And we've got all these websites coming on. So Leopoldo's over there in Brazil, he goes over there and he goes to www.gocloudcareers.com, and Leopoldo gets routed to the web server in Brazil because it's the lowest latency. Now I go to the web server, www.gocloudcareers.com, and I get sent to the US-based web server. Now Eva Doikje, who's over there in Europe, goes to www.gocloudcareers.com, and she gets sent to the European website. And it's based upon latency. What's the time it takes to actually get from point A to point B? Kind of keep that in the back of your mind. That's called latency-based routing. Now, there's another way we could do this geographically speaking, but this is based on latency. So it may be that geography, latency, or anything else. Now, there's another kind of routing called failover routing. So here's what this is. AWS is your primary data center. It's running great. AWS has a power failure, and their systems are down in multiple regions, and poof, DNS says, are you there, are you there, are you there? And it switches you over to Azure, and everything's up and running on Azure. So that's failover routing. Failover routing will shift you from your data center to your disaster recovery on the cloud, from your single cloud to another cloud. And by doing it this way, you can build robust, healthy, multi-cloud, high availability, high performance systems, which is what I do. I would never put it on a single cloud because I know that if the cloud fails, my customers are dead in the water. And I deal with hospitals, and if the hospitals were on Amazon and Amazon had one of the kind of outages they had, patients would die. And imagine a 911 dispatch center where it goes down, people die. So single cloud is not acceptable. Now, it's not just AWS. Azure had a massive outage, and so did Google. These are the best operators in the world, but things happen. So failover routing enables us to use multiple clouds. Of course, we could use weighted routing and send 50% to AWS and 50% to Azure too. Or latency-based routing, it's quicker to get to Azure, quicker to get to AWS. We're using DNS to create more robust environments. So the next one is geolocation routing. And geolocation routing is pretty cool. So let me give you an example. Let's say we're in Africa or Europe, I don't care. But let's say we're in Africa. In Nigeria, for example, they speak multiple languages. You got an Arabic section, an English section, Yoruba, and a few other languages. But let's just talk about the English and Arabic. If you've got someone that's in an Arabic region and you can pick up their IP address and you can send them to an Arabic website, that'd be great. Likewise, if you want to send somebody to an English website because they speak English based upon their IP address, based upon the region they're living in, that would be great. Or, for example, I'm over there in Europe. I'm in Greece. Somebody determines my source IP address and they send me to a Greek web page. I leave Greece and I go to Italy, they sense my IP address and they send me to an Italian web page. Think about some of these regions in the world where 3 and 4 languages are spoken. Wow. Detect your IP address, send you to the language and the right website of your choice. How cool is that? I'd love to go to Greek websites all day long. It'd be fun. But, we all speak our own natural language at home. What are we most comfortable with? Which is actually English, but I just like speaking in Greek because my mother-in-law taught me, and she told me never to forget it. And I'm afraid because she's the sweetest woman in the world and she's loving, but she doesn't want me to forget Greek. So she taught me Greek and I speak Greek all the time, but that's neither here nor there. So geolocation is going to look at your source address and send you to the right place. So that's what we're talking about. The last one is something called geoproximity. Geoproximity routing is about the ugliest thing. I'm just going to read it to you and describe it to you. Geoproximity routing lets Amazon's Route 53 route your traffic to resources based upon the geographic location of your users and your resources. Here's what happens. You look at this giant map and you create a bias section to create some sections more preferred than others. And ultimately what you get is you get something that looks like this. I took this directly off the AWS site. You can shrink these regions 1, 2, 3, 4, and 5 by affecting bias, and that's going to affect your traffic. Now, I know I mentioned it before, the health check, and everybody knows Mike for health checks because apparently my "Are you there? Are you there? Are you there?" was seen all over the internet. Never would have thought of it, but who knows? So when we're dealing with Route 53, it's basically the "Are you there? Are you there? Are you there?" So now think of it. We've got AWS and Azure. Are you there, AWS? Yes. Are you there, Azure? Yes. Are you there, AWS? Yes. Are you there, Azure? Yes. Are you there, AWS? Yes. Are you there, Azure? Yes. Are you there, AWS? No. Azure, are you there? Yes. Are you there, AWS? No. Are you there, AWS? Yes. Are you there, Azure? No. AWS? No. Are you there, Azure? Yes. All traffic gets rerouted to Azure. And now you don't have outages. So that's what you're going to use in a multi-cloud environment for your web-based applications. Also, you'll be using BGP as well. So keep that in the back of your mind. Let me show you what it looks like in a picture. I had somebody draw me a pretty picture. Here's what it looks like. Hey, are you there? Yes. Are you there? Yes. Are you there? Yes. Hey, are you there? Nope. Get rid of this guy over here. Okay, so tomorrow we're going to have all kinds of fun stuff. We've got so many cool, wonderful things to talk about tomorrow. We'll get into some load balancers. We're going to have some AWS services. I think they're tomorrow. Let me check. Got a lot of load balancers. Oh, we're going to have some security stuff tomorrow too. How fun. So if you guys are good and you want me to, I might even teach you how to do enterprise grade security at the same time. So, or maybe we'll save that to our special application lesson. So, Chris, does anybody have any questions for me? I want to make sure we end the day strong. I want everybody to be happy. I want everybody to learn something. I want everybody to have the best experience.
Give me just 1 second.
Sure. When we say in a proximity placement group, there's clustered placement group, partition placement groups, and spread placement groups. So they're all about proximity. But if it's in a clustered placement group, your virtual machines might all be on the same physical server, which is kind of scary. Fast networking, but kind of scary. So that's what it means. Partition placement groups means it's spread across multiple data centers. And spread placement groups means it can be across region. So clustered placement group, all on a rack. Partition placement groups spread across racks. And spread placement groups are spread across data centers. Chris, you want to bring in the next one? Ciao, exactly. DNS is called Route 53 for AWS. The rest of us call it DNS. Of course, Azure and all those other people have their own names too. But yes, ciao. Chris, bring in the next one, please. Can you please explain use cases where the TTL and when reducing? So yes, we're going to spend a lot more time on TTL when we talk about CloudFront and content delivery networks. Here's the thing. Let's just say you've got a cache. If I have the TTL of a month, I put up a picture of cindythecat.com. It gets cached throughout the rest of the world. And it's accessed first by me in Florida, cindythecat.com. And then Chris wants to see pictures of Cindy. And then 5 million people in Florida all want to see Cindy pictures of Cindy. If they all go to the same cache, once I requested it, all 5 million people will get it from the cache, and none of those requests will go to the server, assuming it's there. So the reason we're doing the high TTLs is to basically reduce the load on the servers. The problem with the high TTL is as follows. If I put up a new picture of Cindy on the main page, and my TTL is a month, it could be up to a month until anybody sees that new picture of Cindy. So when we need stuff to adapt fast, we lower the TTL. When we're looking to reduce overhead, we raise the TTL. And actually, Abigail, thank you so much. Please leave a like, comment, subscribe, hit the bell, because that way you'll be notified of all the free stuff we're going to be doing, which is going to be a lot coming soon. Chris, you want to bring in the next one? Eva Doikya, why can I only like this video once? Let me at least just say this. Eva Doikya is one of my students. She's she's got such capabilities. And there's not an interaction I've ever had with Eva Doikya that didn't make me happy. From interactions with her a year ago when she wasn't a student to interactions I have with her now. So thank you so much, Eva Doikya. Angelo, thank you so much. Anycast is the reason you're a CCE. Well, I just love networking, Angelo. It's like, literally speaking, one of my favorite things to do. I started with it in the beginning. I've been teaching it forever, and I just love networking. So thanks so much, Angelo. YH, when you're saying latency between user and Route 53, it's checking your latency to the server. They're looking at your source IP address and determining the latency of the closest server. Great question there, YH. Extraordinarily good. How does Route 53 calculate the latency? Typically speaking, they send an ICMP message to it or a ping and determine how far away it is, but I'm not Mr. DNS. I'm more BGP. Which is best, weighted route into your routing? So Mel, like anything else in architecture, it's always based upon what the business requirements are and what business problems we're trying to solve. So if I'm dealing with a multinational company, I might use geolocation routing because I want my Arabic people to see Arabic. I want my French people to see French. I want my Spanish people to see Spanish. I want my Portuguese and Brazilian people to see Portuguese. I want my Italian people to see Italian. I want my Chinese people to see either Mandarin or Cantonese based upon where they're located. I want people to be seen whatever language they want. In order to do that, that's probably what I'm going to be using them because I want to know where they're at and route them to the right place for the optimal business. But there's time I would use weighted routing every time I was rolling out a new application. So it's really about what the use case is, Mel, and there's lots of different use cases and lots of reasons you would choose both. Chris, if you can bring in the next one. Tech with Mufaz, can I explain why the cloud doesn't offer RAID 5? Sure. So Tech with Mufaz, normally we use RAID 5 for everything. So what is RAID 5? It's striping with parity, right? If we've got 4 disks, write to disk 1, disk 2, disk 3, put extra backup data on disk 4. Next time, write to disk 1, disk 2, put backup data on disk 3, write to disk 4. Next time, put data on disk 1, backup data on disk 2, data on disk 3, data on disk 4. So what we're doing is we're using 3 out of 4 or 5 out of 6. So what we're getting is really good throughput. But when we write the backup data to that additional drive, it takes time to write that backup data. And that additional time takes latency. Now, if we were in the data center Tech with Mufaz, and I have 8 NVMe drives that each have 1 million IOPS in them, and basically speaking, I write to all 8 in one parity data, I'm dealing with still 6 or 7 million IOPS, so it doesn't matter. Now I'm on the cloud, and I've got my provisioned IOPS, IO1 volume, which the max it can do is 64K IOPS. Now, mind you, I can go to Best Buy and for $100 buy 1 million IOPS, but now I've only got 64. So now with these really, really, literally slow cloud block storage drives, if I have to write backup data every time I'm introducing latency, which I can't handle, and the only reason you can't do RAID 5 on the cloud is the disk performance on the cloud is so bad. Elastic block storage, the performance is so bad. Now, all block storage performance isn't good. So whether it's Google or Azure, the block storage is not fast. They want to call it fast, but literally all of you go to Amazon and look up a Samsung 980 Pro SSD drive, NVMe drive. Now go look at the AWS specs and you'll see it's going to smack you in the face. Wow, cloud storage is slow. So when you're dealing with these low performance drives, we can't afford the overhead. So that's when the cloud you can only do RAID 0, RAID 1, or RAID 10. Because we have to overcome the high latency and the low performance of the cloud storage, which is getting better by the day. The new IO2s are literally speaking about half as good or as a $100 Best Buy drive. So they're getting better. Much better, much better, much better. Chris, if you can bring in the next one. When are we getting the BGP?
I was gonna say I put a comment answer, but I figured it'd be good for you to talk about it.
So I want to do the BGP training. I'm either going to do it before or after the CCNA. I'm also going to do a subnetting one. Chris, do you want to put up a website and a sign-up form that we can get everybody to sign up for tomorrow and pick a date? Or do we just want to send a link?
After we pick dates, yes.
Yes. So everybody, here's what we're going to do. We're going to set up a link for the BGP thing where you guys can register. And we'll also set up a link for the subnetting one. And then, because I definitely want to get that back to you, Kev. Wait, when you use multi-cloud, which DNS service will you use? ANS, DNS, third party? Well, I might be using F5. I might be using a third party. I could be using AWS. Reality is, I'm probably not going to use AWS Route 53. I'm going to use something somewhere that's going to be neutral to all the vendors, and I'm probably going to have my own backup devices. So I might have my own F5 DNS, and I might have another service, but I'm always going to use multiple services, and I'm never going to use a single thing. F5's got a great solution, and for most of my customers, I'm going to have an on-prem and multiple cloud because that's what they're demanding. They want performance from me. I don't get asked to put into designs. I get asked to design things for big banks where minutes of downtime cost millions of dollars, hospitals where people die if the connections are down. So when we're dealing with these things, we're not dealing with a single cloud or any non-redundant service. But it's a great question there, YH. And I'll be evaluating the different DNS services every single time. And I'm not Mr. DNS.
And I need you to say something about this. I made an announcement earlier on the channel for our students.
Okay, so Chow, we don't have class tomorrow because we normally have class at noon, and we can't actually reschedule tomorrow's class. So we had the class on Tuesday. We'll go back to normal classes on Tuesday, everybody. And then Friday next week. Mohammed, can we use nested Route 53 on? I'm honestly not sure, and I want to be accurate and only tell you things that I'm sure of. So I'm not sure. Chris, you can bring in the next one.
I'm looking for it. Here we go.
Can you please say more on multi-value routing policy? Yes. Here's what multi-value routing is. I make sure I want to make sure it's what I think it is. Okay, here's what it is. Let's say you've got 5 web servers, and you had a roll of dice, and you flipped it up in the air, and you said, "Oh, Lens, send to server 1." Flipped it up in the air. Oh, send to server 1 again. Send to server 2. Send to server 6. Back to server 1. So multi-value router is just randomly figuring out which server you're going to send it to. So random, I don't think, is a good strategy for anything. So I wouldn't use multi-value routing for anything. I like to plan how things work, orchestrate how they work, know how they work. When you leave stuff up for random chance, it's kind of like using hope as a management strategy. So I don't design architectures like that. But it's a great question, Maria. Thank you.
And that's the last question for right now.
Okay, great. So there was one question I saw that popped on where people were asking for the link for the CCNA course. So if you could kind of make sure we can help people with that.
I just put that in there.
Okay, perfect.
Yep.
Fantastic. So does anybody else have any questions? Thank you so much, Carl Jr. Jazz, I'm so happy to see you here. I didn't see you were there. Charles, thank you so much. Super, be thrilled to work with you. Yes, and our paid training is pretty deep. Thank you so much, Kerfield Lou. And if I mispronounce your name, I am so sorry. I'm just so thankful you're here. Kef-Yala. I'm just so thrilled you're here. Rajesh, thank you so much. I'm thrilled you're here as well. Ivadaikia, thank you so much. Thank you for everything, Ivadaikia. And Habagelmax, again, thank you so much for everything. Another wonderful cloud architect. Yes, please don't forget to smash that like button. Like, subscribe, tell a friend. And we'd like to add more subscribers that we can help. Elvis, so nice to see you. Thank you, KF Yellow. I'm so sorry, but I'm just thrilled you're here. Chris, you can bring in the next one. Hand of God, peace to the Go Cloud Careers family. Thank you so much. Well done for such a great job you're doing. I stand up, salute you all properly at once. Thank you so much. I am so grateful for this, hand of God. I am supported by some amazing students. I've got Leo, who's one of my cloud architects working for me on this call. I've got Chris, who's my COO. As you can see, those people that are blue wrenches do incredible, incredible cloud architects. And so many of my wonderful students are also still here. So welcome all of you, and thank you all so much. Hey, Barrow, when you say your TTL, say 4 hours to 1, does this update replicate around the... I'm not completely sure I understand.
Around the world.
If your TTL is 4 hours, it could take up to 4 hours to everything to be notified. If you change it to 1, in the future, things will be notified much faster. But I'm not Mr. DNS. When you deal with networking, you deal with your routing people, your switching people, and your sysadmin type stuff that do the DNS, and that's them. Thank you so much, Leo. Jamal, thank you so much. I'm so happy you were here, ANGWE. Please go back and see days 1 and 2. Please make sure you get your free copy of that book. I want you to have the best career. Thank you so much, Leonardo. I was trying to run it like a conversation intentionally because I want you all to get it. I want you to all to experience it, so thank you. Thank you so much, Soga, and thank you for all of my blue wrenches. Thank you so much, Robert, another great cloud security architect. Mel, another one of my students, so great to see you, and thanks so much. Thank you so much, Richardson. We're thrilled to see you and have you here. Cecilia, thank you so much. Wow, this is great seeing you all. Let's do this. I love knowing where you're all from. Could you tell us where you're all living right now? Because it's super exciting to me. I love seeing it. Chinton, thank you so much. Thanks so much, Abigail. I really, really, really appreciate this. You know what I appreciate more, Abigail? I appreciate how you and Eva Doikia and Leo and Mel and all of you have created a family. And Jazz, VNHG is part of this family, and you all work together in so many ways. I love that. Tech with Mufasa, Nigeria, fantastic. Texas for Chow, who I know is Vietnamese. Richardson's in Atlanta, and I'm about knowing him by his name. He's obviously has a French last name, Al, fantastic. Madison, Wisconsin, woo. Kenya Carr, Atlanta, Georgia, but I know she's lived in all kinds of great places. Mel's in New York City. Kay Terry's in Washington, D.C., great place. I've got a best friend there. Tamiya, Nigeria, fantastic. India, loving this, love this, love this. Virginia for Raphael. Lagos, Nigeria for Soga. Wow. Raphael's born in Poland and living in the UK. This is just amazing, amazing. Charles in Virginia. I live in Atlanta, Georgia. Thomas in the Netherlands, fantastic. Originally from Ethiopia, now in Virginia. Wow, in Virginia, you're so close to DC, which means getting Sparrow and Burberry and all these great things is so easy for you. You're very lucky. You're from Winnipeg, Canada. Fantastic. And another Lagos, Nigeria. I'm loving this. North Carolina, fantastic. Ray Burns in Florida. I'm in Florida. Cindy's in Florida. East London in South Africa. Fantastic. Philly, PA. I grew up there, so that's a place I know real well. Rhode Island, haven't been there in a long time, but fantastic. Asheville, North Carolina, but DC. Why was I thinking Virginia? I guess DC. Tejas, thank you so much. K-Cast, I'm so grateful to have you here and participate in this class. From South Africa, but originally from Cameroon. We have so many Cameroonian friends. Actually, we have 49 people volunteering in Cameroon right now. Born in India, living in Poland. Raul, that's just so great. AJ in India, this is so wonderful. Toronto, from Manoj. Mr. Gee in Sacramento. Conrad in London. Leo in Brazil. Phoenix, Arizona, from Marty. Leonardo is Brazilian, living in Germany. Oh, fantastic. Chigo and Viadoikia, Bulgarian and Denmark. Oh, sorry for Hungary. I knew you were over there somewhere. Charlotte, North Carolina. That's a city I almost moved to. And thank you so much. So, Austin, Texas. Fantastic. Thank you so much, Chigo. Margins and over there in Amsterdam. Speedy recovery. Roni so much. Guadalajara, Mexico. I haven't been there in a while, but it was fun. In Birmingham, UK, fantastic, hand of God. San Jose, California, I worked there for years. Illinois for Bob, loving this. KCast, Atlanta, Georgia, fantastic. How many days left? Probably 2 more, potentially 3 more. It all depends on how much we get through and how fast, but you know me, if there's questions to be answered, if there's something to be learned and you want to learn, I'll do it. So we're going to keep helping you out. Great webinar. Thank you so much. Bangalore, India, my best friend's living over there. Fantastic. Thank you guys so much, Agita. So let's do this. Let's all end the day on a happy night. Let's take hashtag Cloud Architect. And then I know we're all here. And if you want to add Cloud Architect and Cloud Hired's my middle name. Everything I do is about getting the world cloud hired. So if you can do a Cloud Architect, Cloud Hired, I say we all celebrate the good day. We take a good night's rest. Tomorrow we do all kinds of fun and cool stuff. And we'd love you to see it. So where am I from, Kumar? I was born in Philadelphia. My family is a cross between Greek as well as Israeli, but I speak Greek in the house. My wife was born in Greek, so I consider myself to be Greek. Thank you so much, Chow. Mark, thank you so much. That I was born in Philly, and that's the only life I know other than Greece. Thank you so much. Oh, I'm loving all these cloud hires. This is just, music to my ears. Cloud architects, cloud hires. Give yourselves a hand of applause. You guys have been putting through some seriously hardcore training. I went into some CCIE level routing stuff while we were doing it. And, it was here. We talked about some architectural things. Oh, Gabriel, so good to see you. Jamal, so good to see you. Amrath. Oh, wow, my God, I'm so happy you're here, Amrath. This is perfect. Charles Simpson, wonderful. Oh, love that. Love that name. Tosin, Cloud Architect. So what a wonderful, what a great day. Thank you so much, Kalinikta. Wow, loving this. Spirit, community, all over. It looks like there's some people asking us to do another interview boot camp. Chris, get that on the schedule. We'll do another free interview boot camp. Thank you so much, Kefalo. Thank you so much, Kumar. This makes me so happy to see all of you here. So, thank you so much. Hello from Italia. Oh, wow, that's great. I haven't been to Italy in a little while, but let me tell you, I always love it when I go there. And Derek Houston, Derek's a rock solid architect out there in California. So, Mr. Gee, loving this. Mel, so good to see you. See you all tomorrow. Have a fantastic night. Be proud of yourselves. Download that free book. Please get that book. Make sure you get to the CCNA class. And Chris, there was a request for us to do another free public interview training day. So can you add that to the list? Put together a web page and get so we can give people the chance to put it together.
Sure will.
It doesn't have to be today, because I know that you and I are working 18-hour days, but I want to be able to get it out to the community by next week at some point, because we've got lots of wonderful people here. They made some requests. Let's make them happy.
So next Wednesday we will be doing the architect design class name. I don't know what to call it.
I'm going to do that on Zoom, right?
Yes, it's going to be on Zoom. So make sure that you register for it, because it's not going to be here on YouTube. It's going to be on Zoom.
Because you guys are going to need to be cloud architects, which means
you got to talk.
Yeah, because you're going to have to ask questions. The most critical skill for the cloud architect is communication skills. Don't ask the right questions, don't get the right information. So we're going to give you an authentic cloud architect challenge. And I'm going to be the CEO, and you're going to have to start like you would a real architecture, because I want you all being great.
Yeah.
And yes, Chris is a superstar. Thank you, hand of God. He is a rock solid superstar.
All right.
Okay, so have a wonderful night, everybody. People are registering already for some of these things. That makes me happy. That's why we do them. The more people we can have, the more of a networking and a cloud computing party. It's the greatest thing. So thank you all. Honored to be and privileged to be here with you, talking about cloud computing, teaching cloud computing. We love you all. We love working with you, and we're so honored and privileged to have you here. So have a absolutely wonderful night. Enjoy yourselves, and we'll see you back tomorrow. Have a great night, everybody. Take care.
Bye.